Hey everyone, and welcome to my data analysis with Python course. This course is designed for complete beginners and will cover everything from importing datasets with pandas, exploring and cleaning datasets, and then building simple predictive models using linear regressions. This full course is a supercut of all 8 episodes posted on my channel. Each episode in this video is broken up by timestamp, so feel free to jump around the video if there are certain topics you'd like to explore. Without wasting any more time, let's get on to the video, and I hope you guys enjoy the series. For this first episode, I want to establish what data analytics actually is, what it's used for, and why you should learn it, as well as getting our project environment set up. This episode will be pretty short, as we're not doing too much coding. However, the next video and the ones after will be quite a bit longer, as we'll actually be diving into a lot of coding. To start off, let's just do a quick overview of what data analytics actually is, and why you might be interested in learning it. If you already know this, or you don't care maybe, you can go ahead and skip forward to the quick project setup. Put simply, data analytics is essentially the combination of statistics with computer science concepts, basically meant to produce meaningful insights or knowledge from datasets. The point of data analytics is to look at sets of data, analyze this data to find patterns or trends, and then use this analysis to make predictions for the future. An example application of data analytics could be the following scenario. Let's say you work for a company that sells gym gear through an online store. Your boss gives you a large set of data regarding the demographics of the people who buy your products, including their age, race, gender, education status, etc. Your goal is to use the dataset to figure out the demographic variables that make someone the most likely to buy your product, and then build predictive models regarding future demographic segments that may help your company market their product better. Why is data analysis such a great field to get into? Well, every company wants to maximize their profits, so a huge majority of companies need data analysts to analyze data in order to make more educated decisions in the future, thus strengthening the company. In fact, data analysts can earn companies millions of dollars, hence why companies are willing to pay a good premium to hire data analysts. In fact, Indeed says the average data analyst salary in the US is around $123,842 per year, and Salary.com says it at approximately $141,000 per year. You won't get to that salary overnight, but this of course will put you on the right path towards getting there. Without taking up any more time, let's actually get into the setup of the data analytics environment we're going to be using for this series. For this course, we'll be using the Python programming language. There are some other languages you could use, like R, however Python is our language of choice for this series, as I believe it to be the best language overall for data analytics. You don't need to have an incredibly deep understanding of Python in order to do well in this course. However, I do recommend you check out my Python coding tutorials if you've never touched Python before at all. This course is not a tutorial for Python, rather it is a data analytics course merely using Python as a tool. To set up our environment, head to Google Colaboratory. Colaboratory is actually the exact program I'm in right now, and it's what I use to actually make these text boxes here. You can access it via colab.research.google.com, or you can just go into the Google Suite menu and scroll down until you see Colaboratory because it is a Google tool. Log in with an email if you haven't already, and then create a new file. You should have a screen with just one empty code block, and this editor is where we'll be writing all of our code. Colaboratory puts codes in blocks, and you run each block individually. For example, let's just go ahead and go up here. We'll make a new code block in this top left little block here. It says plus code. Make a new code block, and let's just type, we'll just say print hello YouTube. And then I can run it by pressing this play button, and then it'll run whatever code is in this chunk, and so it does, and it prints off hello YouTube. Now, if I create, let's say, a new code block, and then in this one, I'm just going to print something like hello world, and then I run this block, it'll only print out hello world and not hello YouTube, because it only runs one block at a time, and you run each block by just hitting the play button on each block, so it's pretty simple. Throughout this series, we'll be using comments to help write in English what our code is doing. So to do this, in the code block, we can basically just type this little pound symbol, and then that basically marks it as a comment, so it won't be interpreted as actual code. So then, in this line that has the pound symbol in it, you can kind of just write whatever you want. So I'll just say, like, this line prints out the words, hello, YouTube. So you might see something like this quite often if you're looking at docs, basically just a way to kind of document code and what each thing is doing. If you want to dedicate a large amount of text to be a comment, you can instead create a text block instead of a code block just with comments inside of it. So to do that, just go up here and we see like the new code block, just look to the right of it and there should be an add text cell. And you can just add it like this, and there's a little text editor that just pops up here. These blocks are just meant to be generic text boxes that can be used to explain processes or whatever else you need, and there's no option to run it because there won't actually be any code inside of it. All the stuff up here that I wrote, all up here about data analytics, was done with a text block rather than with a code block. And within any of these blocks, you can actually go click on them, and there should be a little gear on the right-hand side that pops up. And you can open a settings menu. You can kind of customize the blocks however you want, and just to kind of get it to your liking. In the next video, we're going to start to actually explore some beginner data analytics concept using Python, and we'll actually begin the coding journey. So I'll see you there. Hey everyone, and welcome back to our Python data analytics series. In this episode, we're going to explain what data is and what it looks like in the context of data analytics, what libraries we're going to be using, and the idea of data frames and datasets. Before we get started, I want to do a quick overview of the types of data we're going to see in this course and that you'll likely see in the future. So there are two main types of data generally, numerical data and categorical data. Numerical data is exactly as it sounds. It is data that is represented by numbers. And generally, numerical data is broken down into two subtypes of numerical data, and that's discrete data and continuous data. Discrete data is data that can only be certain fixed values, whereas continuous data could have an infinite number of values. So what do I mean by this? Let's look at some examples. If we were to say count the number of students in a classroom, for instance, we could only have whole numbers like 1, 5, 10, 15, etc. It wouldn't make sense to have something like 1.47. Therefore, students in a classroom would be discrete data. Another example we could use would be looking at shoe sizes. Shoe sizes are only made in increments of 0.5, like shoe size 7, 7.5, 8, 8.5, etc., meaning we couldn't have a shoe size of 7.36, for instance. So this is another example of discrete data. If we wanted to look at an example of continuous data, we could actually just look at the height of 50 students in a classroom, for instance. So technically, each student could have any possible number between the normal human range. For example, one student might be 5.139684 feet tall, and another might be 5.8964 feet tall. They could also be 6 foot tall even, but it's still continuous because it could be any number along the scale. Another example of continuous data could be, let's say, distance traveled in a race, for instance, as it could be infinitely measured by millimeters, centimeters, meters, kilometers, and so forth. Here's a really good graphic I found showing how discrete and continuous variables look different. So if you see discrete variables on a graph, there can only be points at actual set intervals, whereas with continuous variables, they can be represented as a line because the data could appear at any point in the line, even if it's a ridiculously precise decimal. So now that we've covered the idea of numerical data, let's move on to categorical data. So that's the other type of data, which are basically just categories, typically just represented by words. So for example, if in a data set every row had either red, green, or blue as a variable, this would be categorical. Or if every row is either labeled, low, medium, high, or let's say short, average, tall, these are also categorical variables. A very simplistic way to think about it is that typically when you see numbers, that's numerical data, and when you see words, that's categorical data. Although it's not always 100% true all the time, that'll generally be the case. So now let's start off by going over what data is in data analytics and what it actually looks like. So data is merely just a collection of information. It can take many different shapes and forms. Many large sets of data you will deal with in data analytics from either Excel files or just general CSV files, which I will go into more detail about later. The idea is that data is usually laid out in a simple table format, which we could call a database table. Let's look at an example. So this table that you see here, which I got from the W3 Schools data science section, has a couple of attributes we should take into account. Like any table, it is split into rows and columns. The rows represent each individual entry. The columns represent each individual variable or attribute. So duration is a variable, average pulse is a variable, hour sleep is a variable, etc. Let's assume for the sake of this data that each row represents one person and their corresponding workout variables. So for example, person 1 worked out for 30 minutes and had an average pulse of 80 and a max pulse of 120. They burned 240 calories during their workout, worked for 10 hours in a day, and slept for 7. This is one entry, and each individual person has their own data. As a data analyst, this is typically the format you're going to be working with data in. Sometimes you may have to make the tables yourself, but all basic dataset tables will have rows, which are the entries, and columns, which are the variables that you're looking at. One question we may ask as a data analyst is, do people who sleep more hours in a day burn more calories during a workout? Or another question could be, do people who work more hours in a day work out for more or less time on average? So now let's do what we're all waiting for, and let's start some actual basic coding. So I'm going to go ahead and make an actual code block down here. And the first thing I want to do is just write import pandas as PD. If you look at nearly any Python data analytics program, you're going to probably see this line at the top, and I'll explain exactly what it means. Pandas is the most popular and well-known Python library for data analytics. Python by itself doesn't have spectacular capabilities for data analytics, so it often relies on third parties to make tools to make developer lives easier. Pandas integrates seamlessly into Python code and allows us to do all sorts of operations on data. By writing this line, we're importing the pandas library, like this, into our code, and we're just giving it the alias of PD, meaning that whenever we want to reference a library, we can just use this PD acronym. We've talked about data, so let's look at what a Python interpretation of data may actually look like. Most of the time, we're going to be using data graphed from an external source. However, let's quickly make our own data set so we can go over a couple of things. I went ahead and took the time to turn our exercise table into a format that's readable by pandas. So I'm actually going to make a new code block down here, and I'm just going to copy and paste it in. And it looks like it's kind of a handful here, but I'll explain exactly what this does. So basically all we're doing here with this data is just making one big dictionary that has keys as the column titles like duration, average pulse, etc. And then each value for the corresponding key is all the values within that column in the format of a list. So if you're not super familiar with how like dictionaries or lists work in Python, it won't be a huge deal because this data is just for show as of right now, but it may help to watch my previous Python video on dictionaries and other multi-value data types. So we can use all this data. Let me actually just make a variable here. I'm going to call it just my data and set that equal to all of this dictionary right here, which should be just this above table, like I said. And then what I'm going to do is I'm going to go to here, make a new line, go down a little bit, and then I want to call the pandas object, and we're going to make a little data frame here. So I'm just going to type this and I'll explain what it means. So I'm going to do df equals pd dot data frame, and then I'll do data equals my data. So basically all we're doing here is making a new variable, calling it df, which stands for data frame, and then we're setting it equal to a pandas function call. We're accessing pandas by typing pd and then calling the data frame function that pandas has, which will actually build a data frame for us. This function takes in one argument data, and we're just passing in the my data variable, which is just this dictionary right up here. And actually, so our program can actually recognize this call, let's actually run this line of code where we're importing the library, just so it doesn't get confused. So what actually is a data frame, you're probably wondering. A data frame is just a structured representation of data, in most cases just meaning a table of data. Think of it almost just as a synonym for a data table, and it's how we interact with data in Python. So if we want to actually print out the data frame so we can actually view it in pandas, we can just make a line down here, and we can actually just type the name of the data frame. So we can just type df. In normal Python, you would normally wrap something in a print statement like this. You do like print df like that. However, pandas makes a really nice table for you if you just type the name of the data frame. So if I just delete this print here, do this, and then I run this, it might take a second, you'll see it actually prints out a data table in an actual data table format, which looks identical to the table that we have right up here. But now that we've put in a data frame in pandas, we're actually free to interact with it as we please. One thing to note is that every row is numbered, and you'll notice that the numbering starts at 0 and not 1. This is because in Python and in pretty much every other programming languages, lists of data will always start with 0 instead of 1. So technically the very first row is marked 0, second row is marked 1, third row is marked 2, and you get the picture. Data frames are super useful because it's how we can actually interact with data in Python. Now that we have it established, there are tons of functions within pandas that we can use to manipulate and analyze this data. We're not going to dive into all these functions just yet, but one easy one that can be helpful is the head function, which just prints out the first 5 lines in a dataset. It's nice because sometimes you may just want to check a small portion of the dataset and not have to print out, the entire thing. To use this function, or method as it's technically called, we would do it just like any other object method in Python. To call object methods, we just need to use a dot operator after whatever object it is we're interacting with, which is just a period on the keyboard, and then type the method name with parentheses and pass in any arguments if necessary. So what I mean by that is to call the head function, we would simply type just .head right here. And then if we were to run this, like this, you'll see that it only prints off the first 5 rows of data. And if I actually want to specify the number of rows to be displayed, I can actually type that number within the head here. So if I wanted, the first 6 rows, I could write 6, and then it would print out the first 6. I could do, let's say, 10 rows, and it would do the first 10 rows, and basically could do any number that you want in here, even maybe say like 2, for instance. And if you try and do any number that's actually greater than the number of rows in the data frame, it'll just max out at whatever number it ends on. So if I try and say I want to show like the first 15 rows or something, it'll only show 10 rows because we only actually have 10 rows in our data frame. So hopefully now you should know that a data frame is just a representation of data, and it's how we interact with data in Python. In our example, however, we're simply making our own data set, when in reality you're typically going to be loading data into your program from somewhere else. So how do we do this? Let me show you. So first we need to find a data set that we can actually interact with, or that we want to interact with. One of the best sources for datasets is Kaggle.com. It has thousands of completely free datasets for you to download and interact with. This is where I get most of my data from when I'm working with Python code for personal projects or whatever else. For this tutorial, I found a dataset that ranks all the countries in the world based on the AI Global Index, which is just a benchmark on nations' levels of investment, innovation, and implementation of AI. I'll provide a link to it in the description of the video, as well as a link to just Kaggle.com in general, so you can kind of explore it and look around a little bit. So feel free to work with your own dataset if you want to, but it may help to use this dataset if you're wanting to follow along with the tutorial. If you're doing with your own dataset, just make sure it is a .csv file. .csv files stand for comma-separated values, and it just means that it's a set of data that has each variable split up by commas. Many datasets we're going to be dealing with in data analytics will have this file extension. Once you have the dataset downloaded onto your computer, we can continue. So now we need to figure out how to load this dataset into our code and turn it into a data frame like we have here with this dataset. There's a couple of ways we can do this in Colab, but let's go through probably the simplest way. The first thing we want to do is go to the top of our code here where we're importing pandas. I'm gonna make a new line. I'm gonna write from Google. All right, from Google.colab import files. This is a library from Google Colab itself that helps you to upload files to your code. The next thing you want to do is make a new line and just write import IO, which imports the IO module, which just means input output. Then we'll run this code again so we can import these new libraries. Now let's go ahead and actually just delete this code block here. So because we're going to be actually using a real data set instead of fake data, so let's just go ahead and get rid of it. So now what we're going to do is just go ahead and make a new code block here, and we're going to call a new variable, let's say data file, and then we're going to set it equal to files.upload. So files is the library up here that we imported from Colab, and calling the upload method on it will prompt us to select a file from our computer to download, and then it'll be stored in this data file variable. If we actually run it, it'll prompt me for a file from my file explorer, which I can then click and then look in my files, and then I will go ahead and upload it right here. And then once it's uploaded, you should get this successful message here. And this dataset by default is named AIIndexDB.csv. The only issue here is that because of the way Google Colab uploads these files, it's not readily available as a data frame just yet. We need to add one more line of code that will turn it into a data frame and allow us to interact with it. So to do this, let's make a new data frame, but we're going to use a different pandas function this time. So I'll make a new variable. I'm actually going to, I'll make it in the same block here. I'll call it dataset, and I'm going to set it equal to pd.read_CSV and have parentheses like this. So read CSV is a super common function in pandas, and it's the primary way of making a data frame out of an already existing CSV file. So normally when using the .read CSV function, we can just pass in the name of whatever file we want. So for instance, like our file is named AI_index_db.csv. So normally we could just do it like something like that. However, because Colab uploads files into an actual file object, we need an extra step inside of just the name. So I'm just going to go ahead and take this, and I'm going to copy and paste this line here instead of our read CSV parentheses. So you don't really need to know exactly what io.bytesIO function does, just know that we need this line to make our CSV file readable to pandas. So just copy and paste this for now, and make sure you have the name of the file, which is data file, on the outside of the square brackets, and then inside you have the actual string name of the file. So now, after writing these lines, we should have our data set fully loaded into our code. So I'm going to go ahead and actually just run this right here, and then I'll just go ahead and reselect our data set. So I showed you just a minute ago how we can actually make a data frame and kind of interact with it just by printing it out and printing out the head function, and just kind of seeing what it looks like. And this read CSV function from pandas is actually just turning our file into a data frame. So what I'm actually going to do to test it out is go ahead and just make a new code block here, and then I'll make underneath this one because I don't want to run this block and have to re-upload the CSV file every single time I want to run the code and test something. So in this new block, I'm just going to go ahead and write dataset like this. Assuming you execute the blocks in order, the blocks at the bottom will know every variable mentioned in the blocks above it. So this block will know that by typing the dataset, we're referencing the dataset variable we made at the bottom of the first block. So now let's actually see what our dataset looks like. So if we go ahead and run this block of code, you'll see that it now prints out our new AI dataset as a data frame in a very similar format to how we saw our exercise data frame being printed out as well. If we wanted to read this, this first row, for example, we would say the United States has a talent score of 100, infrastructure score of 94.02, development score of 100, total score of 100, and it is in the high income group, just to name a few of the variables. So one thing you'll notice here is that there's actually 62 total entries, but it's only showing a couple of them and it's not showing the whole thing, hence these, these dots here in this row to basically show all the overflow. There's actually a really unique feature that Colab has. If you click this little enhance little magic wand button here at the bottom left, if you click it, it actually kind of turns your table into more like an Excel table looking format, which is kind of interesting to see. But just so we can go back to our default one, let's go ahead and just run this again so we get the normal looking table in Colab. So I mentioned it before, but if you just print out the dataset and don't specify how many lines you want, it'll just print out the first 5 and last 5 lines of the dataset, like I said with the overflow here. Just like we used before, we can actually use the head function on this data frame to specify how many lines we actually want. So if we just run it by itself, it'll print out 5 lines. So if you do something like this, like head, run it out, it'll print off the first 5 lines. If we want to say print out the first 3 lines, we can actually specify in the argument and say 3 right here, like that. Or let's just say, we want the first 10 lines, we can just push in 10 right here. Alternatively, just as we have a head function to print out the top of the dataset, we could also use the tail function to print out the bottom of the dataset. So it does the same thing as head, but in reverse. So if I just called, let's just say dataset.tail like this, and I ran it, it would print off the last 5 entries in the table by default. And if I did, tail and I put it in 10 for the parentheses here as the argument, and I ran it, it would print off the last 10. So it's the exact same concept as head, but just reversed. So you have head showing the top and then tail showing the bottom, basically. Now we have our data set ready to go for our code. We're going to cut this episode here before it starts getting too long and save the next steps for the next episode. In this episode, you learned what a data frame is, how to take a data set from online, upload it into Google Colab, and use the read CSV function from Pandas to turn a data set into a data frame. In the next episode, we'll start to get into the actual exploration of the data. So I'll see you in the next one. Hey everyone, and welcome back to our Python data analytics series. In this episode, we're going to go over the concept of data exploration. We'll learn how to view data to get insights from it, ways you can select specific data from your dataset, and also ways in which you can manipulate data in such a way that it makes it more understandable. In our very last video, we obtained a dataset from Kaggle that gives us the AI global index for all the countries of the world. For the sake of staying consistent, we're going to be using the same dataset for our episode today. If you need help getting this dataset, check out the previous video or look in the description for the dataset link. I went ahead and copied the code chunk where we loaded in our dataset from the last video, and already ran it and selected the CSV file. Make sure you do this each time you're relaunching Colab or reconnecting to it. I've also just made a quick dataset.head block here, just so we can get kind of a glimpse of what our dataset looks like and what we're working with, just like we did in the last episode. So let's go ahead and run this just so we can print off the first 5 lines of our dataset. We have all the code set up to load our dataset in and view it using the head function. And now we should look at the next step in the data process, which is using functions to help us view and select data that helps us better understand our dataset. Before we do any sort of manipulation of the dataset or explore any other functions, let's use an easy Pandas function that gives us a good overview of the dataset. So Pandas actually has a describe function that shows things like the mean, standard deviation, and percentiles of each variable in the dataset. So I'm going to scroll down here to where we have our describe function comment here, and I'm just going to call dataset.describe like this. And then if we run this, it'll print out a very nice and concise summary of your dataset and each of its variables. So for example, we can see that the mean value of operating environment is right here, 66.92. And then we could say, for instance, okay, let's find the 50th percentile of infrastructure, and it'll be 65.23 like this. So note that the describe function only prints out the columns that have numerical values, since we can't do this kind of numerical analysis on, for instance, the region column where we just have words like low, medium, or high, because it wouldn't make sense to find a mean for things like those. So this describe function is really useful to give us an idea of what our data actually is and what each field looks like in terms of its statistics. The thing I usually look at with this table the most is the mean, min, and the max typically, because the mean is good just because it gives you an idea of what the actual average value is per field, and the min and max is good because it gives you an idea of what range the numbers actually fall in, and can also potentially signal some outliers too. I would definitely recommend using this describe function on a dataset if you're just getting started with it and need a starting point. As data analysts, it's often necessary to take a look at just one column of data. Similar to how we access any object properties in regular Python with square brackets, we can do the same with the data frame in Pandas. So let's go down to our singular column selection, comment down here, and I'm just going to make a new line. I'm going to type datasets, and I'll do square brackets, and then as a string, I will pass in the column talent. So if we actually run this, you can see that now it just prints out every value of the talent column in order. So if we actually just scroll up and look at the talent column in here, you can see that all the numbers match. We have like 100, 16.51, 39.65. Go down here and it's the exact same thing, because when you select it like this, it is literally just printing out the talent column. We can do this with any variable we want. We just need to make sure we use the square brackets to access it and type in the correct name of the variable or the column. If I wanted to list out all the values, let's say for research, I could just replace talent with research like this. And then I could run it, and it would do literally the exact same thing, just with the research values. One thing to make sure of is that the word matches exactly what the title matches. So like research here, we need to make sure you have a capital R, just because it is capitalized up in here. If the cases are off, it won't recognize it, and it'll throw an error for you. So one thing to note, however, is that it may be difficult to tell which value actually corresponds to which country, since the countries are what identify each individual row. So to help us look at this a little bit better, let's select just the country and talent columns instead of just the talent column. So we'll look at some multiple column selection here. So to do this, I'm going to go into this multiple column selection block here, and we need double square brackets instead of single square brackets if we're going to select multiple columns instead of just one. So what do I mean by that? Let's look. So if I want to select multiple, I'll do dataset. I'll do the same brackets as before, except if I want to select multiple, I need to do double like this. And then I can pass it in kind of like a list, and I'll just say country, comma, talent. And this is because we need to use square brackets to actually access the columns, so that's these yellow ones here. But then we actually also need to use square brackets to denote a list, which are these purple ones right here. So if I go ahead and just run this, you'll see it prints out both the country and talent columns. This gives us a super easy way to see all the talent values for each country. One neat thing you can do with this kind of thing is save subsets like this inside of a new data frame so you can easily reference it in the future. So instead of printing this whole thing out, we can just make a new variable. Let's just say, we'll just call it like talent data frame for right now. And then we can set it equal to all of this. And then anytime we want to see this data frame again, we can just access this talent data frame by just writing its name and then running it and printing it out, and it just do the same thing. But I could also access it in like future blocks if I ever needed this data frame for whatever reason after calling this line. One thing that's very important is that we want to make sure that when we're creating new or experimental data frames like this one, that we're not overriding the original data set. If I were to say, for instance, like right here, data set, like that, instead of doing like the talent data frame, then this is actually going to overwrite the data set and turn it into just this data frame with countries and talent. And then if we want to do anything with any of these other fields, we won't be allowed to, so we'll be forced to reload the data set from the very top. So just a rule of thumb, never do this, never pollute the original data. So I'm going to go ahead and just Control-Z that. If you want to make new data frames to help you with insights or whatever else, make new variables for them and then modify those variables however you want. So next, let's go ahead and move on to two of the most useful functions you're going to find in Pandas, which are lock and ilock. Lock is just short for location, and ilock is just short for integer location. So lock uses actual labels to identify rows and columns, whereas ilock uses integers to identify rows and columns. Basically, these are the primary functions you're going to be using to select a specific chunk of data, and how you use these functions varies only slightly. So the first one I actually want to go over is lock, which uses row and column labels to grab data. So if we actually scroll back up to the top here, we can see that in our data set, every row is labeled by a number, for instance, like 0, 1, 2, and then every column is labeled by some word, like country, talent, infrastructure, and so forth. So I'll go ahead and scroll back down here, and I'll explain exactly how lock works. So lock works basically by just passing in the title of the row and the title of the column in order to get a specific value. So let's say, for instance, I wanted Canada's research number. So to do that, I would just type dataset.lock, and I'd use square brackets, and then Canada is number 3, that's the row they're in, and then I want their research value, so I'm just going to pass in research. Within lock, the row always comes first as the first argument, and then the column argument always comes second, and they're always separated by a comma. So basically just looking for Canada, which is row 3, and we're looking for the column titled research. Note that normally when you call a method or function on a data frame, you need to use parentheses. However, with some functions that involve indexing and selection, like lock and ilock, you actually need to use square brackets instead, just like we would with our regular column selection. So now if we run this code and print it out, you'll see that it prints out 30.67 because we asked for the piece of data at the row labeled 3 with the column labeled research. And if we actually scroll up here, we can look at Canada and we're looking for research in this row, and you see it actually is 30.67. So basically anytime you pass in a specific row with a specific column, then you're going to get a single value that's basically corresponding to the conditions, which is going to be a single cell. However, let's say we just want to actually select one row instead of one whole cell. So if we want to do that, we don't actually have to pass in a columns argument. So let's say we want in just Canada in its entirety. I could actually just pass in the number 3 here, and it'll assume we're wanting all of the columns. So if I run this, you'll see that it gives me a table like printout that has all the numbers and everything for Canada. So we have like 31.28 for talent, 77.05 for infrastructure, and so forth. Technically, I could also add like a comma and a colon like this and get the exact same thing if I run it. So if I did that, we get the exact same thing. This just explicitly shows the column argument because if we put a colon by itself, it means select everything. But you could omit that if you wanted, just like this, and it'll give you the exact same result. Let's look at another example. Let's say we want to get the United States number or their score for development. So the United States is very first in the list, meaning they're at label 0. So I could put 0 here. And then I want to get their development number. So I would put a comma, and then I would put development like this. And then if we print it off, you get 100. We can scroll up here and verify that number is right. Like United States of America, development score of 100. So that makes sense. If I wanted to print out just the United States line in its entirety and not a specific column, I could just delete this development string like this to basically print out the entire United States row. So now, what if we want to actually select multiple rows and columns? So one way we could do it involves using commas to separate out different criteria, and the other way involves using the slicing operator just like we would in regular Python. If we pass in multiple criteria for the rows or columns, we're not going to get a singular value, but rather a list of values depending on what we pass in. Okay, so for example, let's say you want to find the research values for the UK, Canada, and Israel. So I'll make a new lock statement here. I'll just type dataset.lock with square brackets, and instead of just passing in one row number, a 3, let's pass in a list of row numbers. So I'm actually going to do another square bracket here to denote a list. I'm going to pass in 2, 3, and 4. And that is because if we scroll up, we can see that 2 is United Kingdom, 3 is Canada, and 4 is Israel. So those are the corresponding row numbers. So if I were to go ahead and just run this, you'll see that it just prints off the rows for the UK, Canada, and Israel. If we do it this way, note that the order does actually matter, because if we type, for instance, let's say 3 and then 2 and 4, and then print it out, it'll print it out actually in that order. So it'll do Canada, UK, Israel instead of UK, Canada, Israel. So the order of these arguments does matter in terms of how it's going to be printed out. Since we're selecting all the columns, this is another example of not having to specify a column argument. Because if we wanted a column, we would type something like this, where you do column and then, some column argument here. So let's say we actually do want to look at multiple columns. We still want to look at the UK, Canada, and Israel. However, now we want to print out values for country, research, development, and government strategy. We can do a similar thing on the columns argument that we did for the rows here by using commas to separate out different criteria. So to do that, let's make another list here, which we'll denote by square brackets. And then we're going to pass in a few strings for our column names. We're going to say country as one. We'll say research for this one, developments, and then we'll type in government strategy. And so then, if we run this and print this whole thing out, it's going to print off the rows that are equal to, actually I'll change this to 2, 3, and 4 real quick. And run it. It'll print off the rows that are equal to 2, 3, and 4, and then it's going to print out the columns that are equal to country, research, development, and government strategy. So because we're selecting multiple criteria for both rows and columns, it makes a neat little table when we run this function. The values in both the rows and columns are sequential in this case, meaning they are all side by side in the dataset. However, we could switch these up if we wanted to. So instead of 2, 3, 4, let's just type in, let's say 10, 20, and 30. And then instead of country, research, development, and government strategy, we could just write something else here. I won't change it for right now, just to show you the sequential things for the rows. But I could just run this and you see now it gives us another table that has Australia, Spain, and Italy. However, if the values are sequential, there is a much easier way to do this rather than listing everything out with commas. We can use the slicing operator from Python to select the data in a more effective way. So I'm going to just go in here and just do Control-Z. Let's just get these back to 2, 3, and 4. And then actually I'll just go ahead and run this real quick. So for the rows, rather than typing out every single number row we want, like 2, 3, and 4, we can instead just write something like this, where we do 2, 4. So why does this work? Well, this is the Python slicing operator, and it selects every number in the given range. So the colon represents every number between these two numbers, which basically means if we're writing 2 to 4, we're selecting every row between row 2 and row 4, including rows 2 and 4 themselves. And we'll actually need to remove these square brackets here if we want this to work, otherwise it'll throw us an error. So we can run it like this, and you'll see it prints out the same thing as the 2, 3, 4, except we don't have to explicitly write out the number 3, because we're just using the slicing operator. So this slicing operator comes really in handy when you want to do a lot of rows but don't want to list them all out. For example, if I wanted to do rows 2 through 10, I could just do 2, 10 like this, and it would print them all out. The plus side of this is that if I wanted sequential entries, like side-to-side entries, I don't have to explicitly type out, 2, 3, 4, 5, and so on. And this rule actually applies to columns in the exact same way. So let's actually remove the square brackets of the columns here. And if we scroll up to the top here, we can see that country, talent, infrastructure, operating environment, and research are all sequential entries, meaning they're all side by side. If I wanted to select all these columns, I could do a slice operator on these as well. So let's go ahead and go down here. I said I wanted to select everything from country to research. So let's actually do something like this. We'll type country slice research like this. So this slice takes everything from country to research, which will include columns like talent and infrastructure. So if we actually run this now, you'll see we have the exact same result as we would if we listed out each one individually. In the same way as rows, it makes it easier if we have many things to enter. So if, for example, we wanted to get everything from research to total score, we can just do something like this. We'll say research, and then, then we can just type in total score like this. And then if we run it, it would just print out every single one of those columns without me having to explicitly actually list out each one with separation by commas. So just so we can go back to what we had before, I'm going to quickly Control-Z this so we have country to research. And basically, long story short with this line, what we're doing, for our first argument, which is our row argument, I'm selecting every row between 2 and 10. And then for our second argument, which is the column argument, I'm selecting every column between country and research. the result is a table matching those exact criteria. So real quick, if you're familiar with Python, you might be slightly confused with the slicing operator because normally the slicing operator includes the number before the colon, but excludes the number after the colon. However, because these numbers aren't actually indices and instead they are numeric labels created by the data frame, both the first and last number in the slice will be included. So like these numbers you see here, these 2, 3, and 4, these aren't technically index numbers, they're actually just label numbers. So when you do something like 210, it'll include both the 2 and the 10, whereas in normal like Python slicing, if you were to do this, it would include everything from 2 to 9, but it would exclude 10. So one thing that makes slicing a lot easier is excluding numbers before or after the slice operator. So if I wanted to select, let's just say the first 10 rows, normally you could do something like this where you say, 0 to 10. However, I don't actually need to specify the 0 at the start of the slice. So if I wanted to actually just exclude it, I could just delete it like this, and then it would print off, actually I'll run this here real quick, so you can see it looks like that, and then if I were to delete the 0 like this and print it off, it would give us the exact same thing, because if you basically omit the thing before the colon, it just auto-fills in the 0 for this. And I can actually do the exact opposite if I want to grab only the rows 10 and after. So instead of writing colon 10, I can actually write 10 colon like this, and it will know that I want all the rows from index 10 to the very end. So basically fills the last thing in here, like auto-fills it. So now if I run this, you'll see it prints out, it starts at 10 and then prints off every single row until the very end of the data set. And easily enough, the same rule actually applies to columns as well. If I wanted to grab, let's say, everything up until the research column, or every column up into the research column, I could actually just delete this country here, like this, and we have colon research, and it would do the same thing since country is in the first column, so it looks something like this. Or if I wanted to do the reverse, I could do research colon, and then that would select every column from research until the very end, like this. Lastly, if I want to select every single row or column within lock, I can just type a colon with literally nothing else. So when I had something like this, where I had 10 colon, it autofills the end number with the last possible number. And then when I did something like this, where I had colon 10, it autofills the beginning number, which is 0. So meaning if I actually just combine those two things together and I just do just a colon, it'll autofill both the 0 and the very end. So basically it'll grab everything in the possible range of numbers. So if I write it and run like this, it'll literally just print off every single row. This slicing operator is incredibly helpful in a lot of different scenarios. However, one weakness it has is that if you want to select data that isn't sequential. For example, if I wanted to select the columns talent, operating environment, and development, there's not a super simple way to do that with the slicing operator. In the case of data like that isn't sequential, it's better to just use commas to separate them out like we did earlier. Otherwise, if it is sequential, use a slicing operator. Now that you have a solid understanding of how data selection works based on specifying rows and columns within lock, let's look at one last thing before we move on to iLock. So what if we want to select given rows based on values within the column? So basically selecting data based on a condition. For example, what if we want to select every single row that has an income group of high? This is what we would call filtering, and it's fairly easy to do and also uses lock. So we'll go ahead in this code block here, and we'll just write dataset.lock with square brackets to go ahead and get it started off. Now we want to select all the rows where a particular column has a particular value. So how do we do this? Well, we can actually use the bracket selection operator we showed earlier to select the column. So I can do something like this. I can say dataset, and then let's say we want to look at the income group column. So I'll just type income group here, again, using the regular selection that we just showed earlier in this episode. So how do we actually narrow this down now? Well, if we want a condition to filter on, we can actually just type something like this equal sign, and then whatever value we're actually looking for. In this case, we want to look for, let's say, rows where the income group value is equal to high. So I can say equals high. So all this line is basically saying is give me the locations, or in other words, the rows where the column income group is equal to high. So if we go ahead and run this line of code, it only prints out the table with countries that have an income group of high. You can actually see that if we look over here. There are no countries in this table that have an income group that is not in the high level. As another example, let's just say we want to find every row where the region is in Europe. We could just change this line here, and we could say region inside the brackets to specify the region column, and then we say where it's equal to Europe. And then, if we run this, it'll only print off countries that are in the region Europe. With numerical values, you can do something really valuable as well. You can actually use like the less than or greater than symbols to select rows based on those criteria. So let's say I wanted to only look at countries that have a development score of over 50. I could replace this column we're looking at here. I'll just replace it with development. Say development. And then I'm going to type greater than 50, like this. And then, if we run it like this, you'll see that it only prints out 3 countries, all of which have a development score of over 50. Note that I could also use greater than or equal to, so I could do like greater than equal to, and I would write it like this, and I could run it, although in this case it yields the exact same results. And in the same way, just like greater than or greater than equals to, I could also use like less than or less than equal to. For instance, I could say countries with development score of less than 50, and if I ran it, it would print out a whole lot more countries, all of which have a development score of under 50. So next, what if we want to actually select data based on multiple criteria instead of just one? There's a way to do this with checking multiple values in a single column, as well as checking multiple values in multiple columns. So the first way we can do this is actually very straightforward, and it's just using the isIn function from Pandas. So let's say in this data set, we actually want to select, let's say we're going to look at the region column, and then we basically want to select countries from Europe and the Americas. So we'll go ahead and have this here, and then what we can do is use this isIn function. So we just type it like this. We would do isIn, and then in here we would pass in the values that we're looking for. So we said we're looking for countries that are either Europe or Americas. And actually we'll make this a list here so it doesn't throw us an error. So we use square brackets like this. And then if we actually run this code, it now prints out all the countries in Europe and in the Americas. So basically all we're doing here is the regular bracket selection. We're selecting the region column and then using this isIn function, using this isIn function to basically check whether the value is equal to either of these values in this list, which are Europe and Americas, and it prints it out accordingly. The nice thing with this format is that we can kind of just mess around with this as we please and add things kind of as needed. So let's say we want to check the region still, but we want to add another region in this filtering here. We'll just add Middle East. I can just add a comma here, and I can just type Middle East. And then if I were to run this here, it would do the same thing with Europe and the Americas, but it would also include countries that are in the Middle East. The other way we could check for multiple conditions within multiple columns would be to use the AND operator like we would in normal Python. So I'm actually going to take this line here. I'm going to copy and paste it, and I'm going to go ahead and go down here and just paste this in so we can have a separate block to show you this. So let's add something in combination with what we already have in this line, which is just selecting the countries from Europe, Americas, and Middle East. We now also want to check countries that fall in these 3 countries that also have an operating environment score above 70. It's actually pretty straightforward to do this. So inside of our lock statement, but outside of our initial condition, we're going to add just a singular ampersand symbol, or I call it the and symbol sometimes, and then we'll select the other column. So we'll do dataset, and then we'll select operating environment like this, and we're going to say where it is greater than 70. And real quick, before we run this, one thing that I realized when testing out this function is that if you have 2 or more conditions like this, you'll want to wrap each condition in parentheses, or else sometimes Pandas gets a little confused with the ordering and doesn't run correctly. So I'll put this in parentheses here with this condition, and then I'll also put this in parentheses here. So basically any condition on any side of the and symbol needs to be in parentheses. So now if we go ahead and run this line here, and we take a look at this data set, you'll see that the only rows that are actually printed out are the ones that have an operating environment score of over 70 that are also located in Europe, the Americas, or the Middle East. I could, of course, switch around any of these variables to mean something different. For example, changing this, changing this greater than sign to a less than sign, which now if we run it, would print off every country that is still in these 3 regions with an operating environment score below 70. Let's do one more example so you get the hang of this. So I'll go ahead and scroll down here, make a new line here, and let's say you want to now print off every country where the infrastructure score is above 50 and the region is Asia Pacific. In this case, we can just say, we'll say dataset.lock, and then we said infrastructure above 50 in region Asia Pacific. So in our 2 conditions, let's just type dataset, and we'll select the infrastructure column, and then we'll say where that is greater than 50, and then we'll do our and symbol just like we did last time, and also parentheses just to make sure it doesn't get confused, and then we'll say dataset, we'll select the region column, and then we'll say where the region column is equal to Asia Pacific. So now we can go ahead and run this code, and you'll see it prints off only countries in the Asia Pacific region that have an infrastructure score of above 50. This method of filtering can be super helpful for trying to look at data that falls within certain ranges or meets certain criteria. If we're using and symbols, we could actually use as many as we wanted to. For example, right now we just have 2 conditions in this line separated by an and symbol, but if we wanted, we could have like 15 or 100 conditions all separated by and symbols. I'm not sure why you'd ever need that many, but the option is there to use as many conditions as you possibly would want. Now that you should know how to use lock to locate specific chunks of data based on different criteria, let's next look at ilock. Ilock works pretty much in the exact same way as lock, except instead of using the labels of rows and columns, you instead use the index number. So let's go down here and we'll actually make a new code block down here. And let's say I want to retrieve the first 4 rows of the dataset and display the development and government strategy column for all those rows. I could write something like this. I could say dataset.ilock 0 to 4 and then 5 to 7. So why did I choose these numbers? So remember in Python that everything you have within list or any like multiple data type things are going to be indexed by 0. So for example, if we're looking at a table of our full data set, which I'll make a quick code block here. I'm just going to print off, dataset.head, pass in 5 just to be explicit. And then I'll run this. And notice that for all these rows, it starts at 0, 1, 2, 3. I said before, these are actually not indices, these are technically just labels. However, we can actually look at it in an indexed way. So in any list-like things, whether it's the rows or the columns, the first is always going to be index 0. So this is index 0 row. This would be index 1, index 2, index 3, and so forth. And the exact same thing applies to the columns. So this column is index 0, this column is index 1, this column here, infrastructure, is index 2, and so forth. So hopefully you get the picture there. So basically for the rows here, when I write 0/4, I'm including everything from index 0 to index 4 here. However, now that we're dealing with actual indices, this 4 is not going to be included in the slice, meaning that we're only grabbing 0, 1, 2, and 3, because in normal slicing, the last index is actually excluded. And then for the columns here, you see we passed in 5, 7, and I said we wanted to select the development and government strategy columns, so let's actually count over the indices here. So country is index 0, talent index 1, infrastructure is 2, we have 3, 4, and then 5 is development here. So development is in column indexed 5, and then government strategy index 6, and then commercial is index 7. But again, because this is the last number in the slice, being 7, it isn't going to be included. So we're actually just going to be grabbing 5 and 6, which is just development and government strategy. So now if I go ahead and run this code, you'll see that it prints out rows 0, 1, 2, and 3, and then the columns development and government strategy. So just so you get the idea of how this works, let's do another example, just so you can understand. So let's say I want to use ilock to select the first 10 rows and display the last 4 columns. So let's make a new ilock. We'll say dataset.ilock, do our square brackets, and we know the first 10 rows will be indices 0 through 10. So we can just type :10 like this. And then to find what we need for the indices of the columns, let's just kind of go ahead and count over. So we want the last 4 columns, including, let's say, region, cluster, income group, and political regime. If we count over the indices, we have 0, 1 with talent, 2, 3, 4, 5, 6, 7, 8, 9. So it appears that region is at index 9. So we said we wanted everything from region to the end, since we're doing the last 4 columns. So we can actually just type 9 and then colon here to select everything up until the end. So now if I go ahead and print it out, you'll see we have every row from 0 to 9, which is the first 10 rows, as well as the region, cluster, income group, and political regime columns. Pretty much all the exact same rules with ilock are the same with lock, so I won't go over every selection we did with lock. However, again, ilock just uses the index of the row, label, and column rather than the name of the label itself. Typically, when I'm doing this kind of work, I like to use lock instead of lock because it is more intuitive to me, and you don't need to count all these label indices because that's kind of an inconvenience in my opinion. Hopefully now you have a solid understanding of data selection in Pandas using lock and ilock, as well as a solid understanding of how general data exploration works. The lessons learned in this video are very essential for being able to manipulate data in the way you want it, so make sure to go back in the video and double check if there are any spots you aren't 100% sure on, especially the section where we went over lock because that'll come up a lot in our future episodes. In the next video, we'll cover the idea of data cleaning and just general mutation. I'll see you in the next one. Hey everyone, and welcome back to our Python data analytics series. In this episode, we're going to explore the concept of data cleaning. So data cleaning is the process of fixing data that may or may not be properly formatted, or even removing incorrect entries or improperly formatted entries. The reason we want to do this is simple. It's difficult to do any sort of actual data analysis on a set of data if there are certain rows or fields that are not formatted properly. For example, if we have a data set with 100 entries, and 10 of those entries have NA or null for some of their values, and we try and find the mean of all these particular values, Pandas is going to get confused because we can't find the mean of a range of numbers that don't actually exist. So NA or null values in your data fields are going to cause weird and frustrating errors, so it's important that we fix these issues before we get into our actual data analysis. The dataset we've been using with the AI Global Index may not be the greatest example, partially because this is actually a very clean dataset with no null or NA values in any of the fields. This is probably mostly in part to the fact the dataset is so small, because we only have 62 lines actually in the dataset, but many real datasets that you might encounter will have thousands, hundreds of thousands, or even sometimes millions of rows in them. However, we can still explore data cleaning in the context of replacing and removing singular or multiple entries. We have our imports up here and the code necessary to load our dataset in, so let's get started. Real quick, before we get started with any actual data cleaning, there's one exploration function I missed out on in the last episode that's actually pretty common, so I'm just going to go ahead and cover it here really quickly, and that's what we call the group by function. Group by is a helpful function that allows us to group all entries that have the same category variables together. For example, let's say you want to look at all the countries with their income group and group together ones that have the same exact value. We can do this by writing dataset, and then we're calling this group by method. We'll say .group by, and then what we need here is to pass in a argument that's by, and then we'll just say income group like that. So basically all we're doing here is specifying our dataset, calling the group by function from Pandas, and then this function needs one argument, the by argument, and then we're just setting it equal to our income group. However, if we run this, you'll notice that nothing actually displays here. So when we're using group by, you have to do some operation after grouping it to actually get a display. So if we wanted to use our describe function from the last episode, we could just add .describe here like this. And now if we run it, see, okay, it prints out, and we'll only have 3 rows, one for each possible category variable. We have high, lower middle, and upper middle. And each one has stats for each particular field. So there's the talent field, and it has, the same thing we had in the describe table. We have count, mean, standard deviation, and so forth. And there actually is some overflow here. And then if you look at, say, a total score, you can see the same thing. And it basically just groups it per each categorical variable. If, for instance, I wanted to grab the mean values of each income group, I could replace this .describe here with .mean instead. And if I run it, it will give us the average value of each variable within each grouping. So, for example, countries with a high income group have an average talent number of 20.33, and let's say countries that have a lower middle income group have an average research value of 3.21. So this is super useful for partitioning categorical variables to draw some conclusions, and we're going to actually explore this group by function a lot more in a future episode as well. And this is also the first instance we've seen of what's called method chaining. So when we call methods on Pandas data frames, we can just write one method after another using the dot operator. What I mean by that is up here I have dataset.groupby.mean. And if I wanted to add more, I could do like something like .head like this, and then after that I could do like .filter and so forth. It does each method sequentially, so you don't need to worry about having a line for each individual method. You can lump it all into one if you want. But for now, I'll just go ahead and delete this just so we have it back at the mean. There may come times where you need to replace pieces of data in your dataset. Maybe the values you have currently are formatted in a bad way, maybe they are extremely long strings that need to be shortened, or maybe they are just misinputs that are simply incorrect. Whatever the case may be, replacing data in a dataset is an essential skill to know. But before we replace any data, I made a point in the previous episode that you should never pollute the original dataset. So to follow this point, let's actually go over dataset copying really quick. So I'm going to actually make a copy of dataset. I'm going to call this one mod data. And then to make a copy of a dataset, we should just type the name of the dataset that we want to copy. So we'll do dataset and then .copy like this. So we're just calling a copy method. And if I actually don't write this copy, it'll basically just create an alias for the original dataset, which means if we edit the mod data, it'll actually edit this dataset too as well, which we don't want. We don't need to make a copy of the dataset each time we want to change something. We just want to make sure at the beginning we make a copy, and then we can edit this copy kind of however we want. So I'll go ahead and just run this here so it's copied, and now we're good to go. The first thing we want to look at for data replacement is a simple replacement of a single value in a dataset. In our last episode, we explored the lock and iLock functions, and those functions are extremely helpful when it comes to data cleaning. Hence why I went over them in the last episode. Let's apply them in this episode though. Let's say, for instance, we want to change the value of the United States research. Obviously, we don't want to just randomly be changing data for no reason, but let's assume theoretically this number is faulty for whatever reason there may be. So to do this, we can use the lock function to select it, and then use an equal sign to change it. To show you what I mean, let's type it out. So I'm going to go into this cell here, and I'll type it out just like this. So like I said, we're going to use the lock function to select, so I'm going to do .lock, and the United States is at index 0, so I'll select the first row, which is 0, and then the research column. And then all I need to do to change the value is set it equal to something else. So I can say equals 50. So basically all we're doing is selecting the value we want to change and setting equal to something else. If we actually print this off now, or sorry, I'll go ahead and just print like this. I'll print this off. And then now if we run it, if we look at the value of research for the US, it is now 50 instead of its default value of 100. So just so I don't actually mess up this data set, I'm going to change this back to 100, but you get the picture. Actually, for instance, real quick, show you something else, like 75, that's changed here. We can do like any number really, and it'll be replaced with that value. But I'll change it back to 100 here, just for the sake of consistency. So this way of data replacement can be useful from time to time, but if we have many entries that need to be changed, typing the log function just for individual entries and changing them all manually is going to take an unreasonable amount of time and will be super inefficient. So luckily we have a solution for that. So the first function we're going to use is simply just called the replace function. And like most of our other functions, it comes from pandas. The replace function works like this. It takes in two values. The first value is the one you want to replace, and the second value is the one you want to replace it with. So it seems simple enough. Let's get into it. So let's say for whatever reason, we look at our data set here, and we see that this is titled Asia Pacific for all the countries in the Asian continent. So instead, we just want to have it say Asia because that's more readable and easier to type out. So to do this, let's actually go into our multiple data replacement cell here, and I'm going to call our mod data dataset, and then I'm going to call this replace function on it. And then let's just pass in two values. So like I said, value 1 is the value I want it to be replaced, which is Asia Pacific. So I'll just type Asia Pacific. And then we want to make sure this type exactly how it appears. And then value 2 is the one you want to replace it with, which is just Asia. Now let's go ahead and just print the head of this real quick. And we'll actually notice something interesting here. If you look at this, you'll notice that it actually didn't change. It is still Asia Pacific. So why is this? So there's actually a third argument we can pass into this function that specifies whether to actually modify the data set or not. And we call this the in-place argument. And by default, it is always false. And this argument here you're going to see is appearing in a lot of different functions that are kind of like modifying and mutating data. So this is useful to know just in general. So basically, if we want to change this and we want to actually modify the data set, we can actually explicitly state that. So we can add this in-place argument here. We can say in-place, and then we could set it equal to true. And then if this is the case, now when we run it, you'll see that it actually does change Asia Pacific to Asia. So really what this in-place argument comes down to is if you want to modify the data set you're actually working with directly, use in-place equals true. Otherwise, if you're making a copy of it and doing something else with it, ignore this argument and it'll default to false. I would just advise you never use in-place true on the original data set to not pollute the data. However, since we have this copy data set here, it should be fine. One quick upgrade we can make to this line is select just the region column. Because we didn't select any specific chunk of data, this line of code right here is basically going to look over the entire data set for anywhere that it says Asia Pacific. The only place we're ever going to see that is in the region column. So I'm just going to go ahead and add a square bracket here like this, and I'm just going to type in region. This is a bit of an optimization thing as it will help your function to run a little bit faster if there are many lines of code, because basically we're just selecting the region column instead of selecting the entire data set. It's always good to be as specific as possible when you're editing data. So let's just go ahead and run it, and obviously it'll be the same result. So next up, what if we get a really large data set and we decide we don't want to deal with some of the variables? Maybe when researching, we only want to look at a couple of the variables and ignore the others. If we wanted to get rid of some of the variables, meaning some of the columns, one option is to do what we did in the last episode, which is use square brackets to specify which columns you want. However, what if you have 100 columns and you only want to delete one of them? You don't want to have to specify the 99 you want, rather you should be able to specify the one you wish to delete, and I'll show you how to do just that. And for dropping columns, Pandas has a really nice function for this called the drop function. You can actually use this function to practically drop anything from the dataset, but for now we're just going to look at dropping a particular column or multiple if we want to. So it's actually pretty self-explanatory how we use this drop function. So we're going to go in this cell here, we're going to type the name of our dataset, so mod data, and we're just going to call the drop method on it. There's many potential different arguments you could pass in here. However, we want to type columns and then equals, and then type whatever column we want to remove as a string. If we go up here and look at our data set, the most important pieces of data are going to be these numbers that we have. So for example, fields like talent, infrastructure, operating environment, and so forth. Let's say, for instance, however, we don't really care about the categorical variables like region, cluster, income group, and political regime. So let's just say for right now, we just want to remove this cluster column. To do that, in our drop function, we would just type the string name of the column. So we would just type cluster like this. And then, just like last time, we'll add our in-place argument to actually modify this mod data dataset. So we'll say in-place equals true. And then I'm just going to go ahead and print the head off here, like this. And then if we run this now, you'll see there's no longer any cluster column because we completely dropped it from the dataset. What if I instead just want to remove not just one column, but multiple columns? If this is the case, we can just pass in a list to our columns argument instead of a single string. So to do this, we can just add square brackets to our argument here. So we would do something like this, and then we can pass in, not squiggly brackets, square brackets. And then we can just pass in multiple column titles as strings separated by commas. And just for the sake of showing you how this works, let's just delete all the categorical or non-numerical data points. So let's just delete region, cluster, income group, and political regime. So in here, let's say region, comma, cluster, and then have income group. And then lastly, we have political regime like this. And one thing we want to make sure of is that the uppercase and lowercase matches exactly what the titles are here, because Pandas is case sensitive and won't recognize the terms if the uppercase and lowercase don't actually line up. So now, if we go ahead and just run this, let's see, we get an error here. It says cluster is not found on access. Oh, okay. So we already deleted cluster, so it's actually giving us an error here. So we can actually just delete that like this, and then print it off, and you'll see that now all region, income group, political regime, and the cluster columns are all gone. And we're actually going to be using these categorical variables later on in the episode, so I'm actually going to go up here, and I'm just going to recopy the mod data just so we can get a new fresh one without the things being deleted, just because we want to use them a little bit later. Sometimes, however, the case may actually arise in your work where you do have columns that are actually just useless to you and just take up space, in which case is a very easy way to delete them. For our very next scenario, let's say we have a scenario where the title of a column is way too long, or maybe just not very descriptive of the data. Well, we have a way to rename column titles that's actually pretty straightforward. Let's say you want to make a new data set where we've renamed the total score column to just total. Here's how we would do it. So to do that, in this block here, I will just type mod data.rename. And then inside of this, we need to specify a columns argument. So I'm going to say columns equals like this. And now, according to Pandas documentation, this columns argument has to be a dictionary, where each key is the old column name and each value is the new column name. So to denote a dictionary, we would use squiggly brackets, and then let's change the name. So again, let's just say we want to change the total score column title to just total instead. So because total score is the actual current name, let's type total score like this. And then as the corresponding value pair, we'll just type colon and then total, because that's what we want it to be renamed to. Let's actually make this a new data frame because I don't actually want to modify this data set just yet. So I'm setting this all equal to a variable called testing. Let's just make one, let's say testing.head. And then if we run this now and we look here, it is no longer total score, it is just total. So we've successfully renamed the column title. What if we want to rename multiple columns? For that, we could just add values to our dictionary separated by commas. So let's say for whatever reason, we want to take this government strategy here and just turn it into govstrat. To do that, we can just add a comma here in our dictionary. We just add it right here. And then we could add something like this. We can say government strategy. And then again, this needs to be a key value pair. So for our second value here, we'll just say govstrat. And then now if we run it, the total score has been renamed to total, and then government strategy has been renamed to govstrat. So our next useful function in Pandas used in cleaning is the drop_na method. It's similar to the drop function, however, rather than taking in arguments for specific rows or columns, what it does is delete every row or every column that has an NA somewhere in it, meaning not applicable or null. So NAs often appear when there are errors in the dataset or if certain fields cannot be calculated or shown based on what the data is trying to represent. As you can see from this dataset, we don't actually have any NAs anywhere, and I've looked over it just to double check. However, it is fairly common to see them in the world of data analytics. However, if I did want to delete any rows that have any NA values anywhere in them, I could simply just type something like this. I could do mod data, I could type drop NA, and it's as simple as that. So by default, this right here will drop all rows with NAs in them. If, however, we wanted to drop columns with NA in them, we could just put 1 in here, and that is actually the value that would signify columns. So 0 is a number that signifies rows, but it actually defaults to this, so we don't need to actually explicitly say 0, and then 1 would identify columns that need to be deleted. I would, however, just caution against using the drop NA function freely though, because sometimes the NA is actually there for a good reason and it makes sense why it's there. So just simply deleting rows outright may skew the data and may not be the very best option for handling this. An alternative option to using this could be the fill_na function. So fill_na just specifies a value to fill NA values with, rather than deleting the rows altogether. This can help to maintain the accuracy of the original dataset. However, we should be careful about what we fill the NA with, as filling it incorrectly could impact our analysis. To fill all NA values within something, we want to call the fill_na method on our dataset. So let's just type mod data.fill_na like this. And then all we need to do is basically pass in the value we want to replace it with. So there's a couple of different ways to fill these depending on what your dataset is. However, one common method is to simply fill NAs with 0 if the field is typically numerical. So to do this, all we would need to do is type 0 in here, and it would fill all NA values with just 0. And just like many of our other functions, there is an in-place argument for this one as well to make sure you modify this data set. So I'll just go ahead and run inplace.true, and then I'll just print off head here. And then if we actually just run this, nothing actually happens to our data sets since we don't have any NA values. But if we did, they would all be filled with the value 0 since we specified it right here in the fill NA method. It's also possible to only select certain columns or rows when we're doing this. So we can use what we learned with lock and ilock last episode to make this easier. So for example, let's say we wanted to fill only the NA values in the columns that have numerical values, which are just talent all the way through commercial. So basically here, all the way through this column here. It wouldn't make sense to replace categorical variables with 0 since a number doesn't make sense for values that typically have words in them. Like for instance, let's just say we took the income group column. It wouldn't make sense to fill an NA here with 0. So let's just go ahead and look at the numerical columns first. Let's look at only talent through commercial and how to replace these just individually. So to do that, all I'm actually going to do in here is just instead of calling in the whole data set, I'm actually going to make a .lock function. So I'm going to say .lock with our square brackets as we normally do. And then I'm going to put a colon here, like I showed last episode, to select every single row. And then I just want to type talents all the way through commercial like this. And then we're keeping this same fill in A, and we're filling in one with 0, and then in place should be true, so we modified this actual data set. So all this line is doing is selecting every single row with this colon here that has a numerical value, so everywhere from talent to commercial. And then it is calling the fill NA function to fill them with zeros if there are any NAs in there. And again, we don't have any NAs if we actually did this, so it wouldn't actually do anything when we run it, but this would be one way to do it. And then if we look at our categorical variables like region, cluster, income group, and political regime, it would likely make more sense to fill those NA values with something other than a number. Maybe we want to replace it with the string unknown, for instance. So to do this, we can do a really similar thing to what we did in this line. And instead of selecting talent through commercial, let's actually just select, we'll say region, all the way through political, did I spell that right? Yeah, political regime. And then we would do the same thing, except instead of having 0 here, let's just fill it in with the string unknown. And then basically all we're doing here is using lock to select all the rows in the ModData dataset, and then all the columns between the region and political regimes, and then filling any NA values with the string unknown. And again, just like before, it won't actually do anything because there's no actually NA values in here. But if there were, it would fill all of these columns here and the rows with the value unknown if it found any NAs. Next, let's look at another example of data replacement that may be super useful for you in the future. So let's say we just look at our data set and we look at these decimal values here. We say, I don't really like that these numerical values are decimals. Rather, I'd rather have them to be integer values or whole numbers instead. So how can we change the type of all these variables? Pandas has a nice function for this known as type. Whatever we do, we want to make sure we're not selecting the whole data set. So let's go down here into our changing value type cell. I'm going to do a lock statement. I'm going to say moddata.lock and then square brackets as usual, colon to select every single row. And then we're going to select everything from talent to commercial, or basically all columns from talent to commercial. And then normally if I was using something like replace or fill in A or anything along those lines, I could just type dot and then the function name, and then I could just do in place true like that to modify it originally. However, this asType function doesn't actually support the in place argument, so I'm actually going to have to do these manually. So I'm going to go ahead and just delete this here. However, there actually is a pretty easy workaround to doing this. What we're going to do is basically just copy this here. We're going to make an equal sign, and then we're going to paste it on the other side. Then on this other side here, we're just going to type dot as type, so we call that method, and then convert to an int. So basically what this line is saying is that all rows and columns between talent and commercial are now equal to the same exact thing, but just changed to integers using the asType method. So now if I were to just go down here and type moddata.head like that, and I ran it, you would see that there are now no decimal values. They're all integer values between talent and commercial. One thing you notice when you're converting from int to a decimal number, or a float I should say, is that it'll simply just drop the decimal. So for instance, Canada, we have 31.28 for talent. When you convert to int, it basically just rounds down since it drops it, and this basically 0.28 just goes away. So now we just have 31 for our talent value. One more thing you want to potentially look out for with your datasets is the idea of duplicate entries. So duplicates are entries that are perfectly identical, and they're important to detect because in some contexts, duplicates, whether on purpose or an accident, could theoretically skew your dataset in a negative way. Obviously, duplicates aren't always bad depending on the context you're working within, but sometimes they can be, so let's actually look at a way so we can remove duplicates within our dataset. A super easy Pandas function to use for this is simply the drop duplicates function. This function will examine every single row in the dataset, and if there are any rows that have the exact same values for every single variable, then it will identify those rows as duplicate rows and it will delete them. And to call it is actually very simple. All we need to do with that is call our dataset, so let's say my data drop underscore duplicates, and then we're going to do our in place equals true here. Every row in our dataset is unique to an individual country, so there's no duplicates in our dataset. However, if we were to run this and there were any duplicate entries, they would be removed. So let's just go ahead and run mydata.head. Obviously, there aren't any duplicates here, but if there were, they would be removed. Okay, the very next thing I want to do is show you how to make new columns based on existing ones. So I'm actually going to make a new code block here. I'll set a comment. I'll just say make new columns. So a lot of times when you're looking at data, or when you just hear the term in general, you talk about research and development. And a lot of times they're kind of grouped together as one thing when it's just called R&D. So let's say we want to make a new column for each country where we just take the average out of their research and development values and just score it to get our own individual R&D column. To do this, we would go down here. We could type something like this and just follow along. So I'll type mod data, and then I'm going to do square brackets here to select, and I'm going to make a new column. I'll say R&D average. I'm going to set it equal to the average of the other two columns. So I'll say mod data, and I'll grab research. And then we want to add them together. So I'll do mod data development. And then, let's see. And then, okay. And then we want to divide them by 2, just like this. So by using square brackets on a column that doesn't actually exist, like R&D average, it'll make a new one if you use an equal sign with it. And here we're just setting equal to the average of research and development, hence why we're adding them together and then dividing it by 2. So now if we just make a moddata.head here and then run this, you'll see it actually did make an R&D column, but it made it at the very end here, but it did appear to work. But it's kind of inconvenient for the ordering here that the R&D average is at the very end because it's after all the categorical variables and not right after research and development. So let's actually make a new code block down here, and let's just say rearranging columns, and we'll explore that right here. So to do this, we can actually use the pandas insert function. So to use it, we'll just type something like moddata.inserts like this, and then we're going to pass in some arguments here. The first argument needs to be the index you want to insert out. So let's count over the indexes of the columns. So we have 0, 1, 2, 3, 4, 5. So it looks like development is at index 5. So if we want R&D average to be right after that, we need that to be at index 6. So let's go in our insert function here and just put 6. And then what's the name of the column that we actually want to move? So let's just enter that as a string. We want to move the column titled R&D average. And then we need one final argument here. If we run it just like this, it'll actually work. However, we'll still have our R&D average at the very end of our data set, so we'll actually have 2 R&D average columns. So we want to remove the existing one. So to do that, we're just going to type moddata.pop and then pass in the name of the column like this. And this little function here as a third argument will actually remove the duplicate. So now we should be good to go. So let's actually just type moddata.head like this and then run it. And now you'll see we nicely have our R&D average score right after development instead of at the very end. So it's now been rearranged to a more correct location. So now you should have a good idea of how to actually just rearrange a simple column like that. I hope you were able to learn quite a bit in this video. In this video, we went over single data replacement, multiple data replacement, dropping and filling NA values, renaming columns, changing the type of single and multiple pieces of data, dropping duplicates, and adding and rearranging columns, as well as just using lock to generally help us select data that needs to be cleaned. Now that we have a solid understanding of exploration and cleaning, in the very next episode, we're actually going to move forward into what's called data visualization. So I'll go ahead and see you in the next one. Hey everyone, and welcome back to our Python data analytics series. In this episode, we're going to go over data visualization in Python, which essentially means plotting graphs in order to see what our data actually looks like. Sometimes just by looking at a dataset table, we're able to draw conclusions on simple things. Like for example, in our dataset, we may say, okay, it looks like the United States has the highest average overall scores through all these scores here, and then obviously the highest total score. Or hey, maybe we look at Canada and say, I'm going to guess that Canada maybe has higher average scores than Israel does. The question then becomes, how can we actually look at our data in a way that makes sense and makes these conclusions easier to come to? That's where data visualization comes in. So data visualization is basically just the graphical representation of data in a way that makes it easy for you to understand and easy for you to communicate to others without them needing to have any sort of knowledge of the data set. Probably the most common library you're going to see in Python for data visualization is called Matplotlib, which just stands for Material Plotting Library. You can find all their documentation on matplotlib.org, which is actually the website I'm on right now, and I'll go ahead and leave that link in the description of this video. They have tons and tons of examples of different types of graphs you can make, and you can click on basically any of these graphs here and get access to the source code for them to implement yourself. In this video, we'll go over a few of the more basic ones to help you get an understanding of how it works. So like Pandas and any other external library, we want to first import the library into our code. So to import Matplotlib into Python, all we need to do at the top of our code is just type this line here. So it'll be import matplotlib.pyplot, and then almost everyone uses the same abbreviation for the import, which is just PLT. So we'll just say as PLT. Then, similar to how we use Pandas as PD, anytime now we want to use the Matplotlib library, we can just use this PLT as a reference object. So first, let's actually just mess around with some plotting using our own data and not from data from the dataset, just to give you kind of an idea of how the plotting works. The first graph we'll make will be a super simple linear function using a basic x and y plotting scheme. So to do this, I'm just going to make two variables, an x variable and a y variable, that will each represent their respective axis. So for the x variable, let's just make something, we'll say x equals list in range, or all numbers in range 0 to 10, and then we're going to make y equals list in range 10 to 20. So basically all we're doing with these is just making a list with all the numbers between 0 and 10 for x, and then making a list with all numbers between 10 through 20 for y. And then to access the most basic x and y plotting function in Matplotlib, all we need to do is just type something like plt.plot, and then we're going to pass in x and y in that order, because the first argument will always be interpreted as the x-axis argument, and the second argument will always be interpreted as the y-axis argument. So then, if we go ahead and run this code chunk, you'll see that it now prints off a very simple linear function on this graph. There are quite a few different customization techniques for a simple line graph. One such example would be changing the color of the line. So in this plot function, we can actually add a third argument. We can add a color argument like this, and then we can set it equal to any well-known color we want. Let's say we want red, so I'm just going to type in red as a string like this. And then if I were to just run it again, you would see it now changes the line to a red line. So it's kind of different, a lot of customization things like this that you can kind of use. And they'll all be separate arguments you can actually just pass into these functions. If you want to see a whole list of the different customization options you have, you can go to the Matplotlib website and check out this function here, this plotting graph, and it'll give you a whole list of things you actually could pass in. So all the documentation is there, and that's where you can look at it. One other important customization thing that I should mention is labels for both the x and y axis. This is a super helpful thing to know. So to label the x and y axis, all we need to do is make a new line, and we'll make plt.xlabel, and then we can make it equal to any string we want, and I'll say plt.ylabel as well. For the x label, just because this data doesn't really mean anything yet, I'm just going to say like insert x label here, and then for the y one, I'll say insert y label here. And then one last thing, by default, the graph will be displayed if any edits like this are made to it. However, if we want to explicitly display it, we can just at the bottom here, just type plt.show like this. Then if we run this, you'll see that it now has labels added plus the color, and it shows the entire graph. So we see insert y label here on the y-axis and insert x label here on the x-axis. Next, let's look at a scatter plot. So scatter plots are going to be plotted in pretty much the exact same way a linear plot would, except that we would just call a different function to graph it. So I'm actually going to take all of this code here, I'm going to copy it, and I'm going to paste it into this. And then I just want to change these x and y variables around a little bit. So I'm going to make x just a list. I'm just going to pass in some random numbers. I'll just say, let's make this up as I go. I'll say 1, 3, 6, 8, and 14. And then I'll make y also a random list of things. I'll say 4, 7, 7, 10, and 12, just like that. And then all we need to do to make it a scatter plot instead of a regular linear plot is just to change this function here. Instead of dot plot, we're just going to type dot scatter. And then if I go ahead and run it now, you'll see that we have 5 dots for each corresponding coordinate. And it does the same thing that the linear plot does, where it sets coordinates depending on the value. So for example, 1, 4 is the first coordinate, 3, 7 is the second coordinate, and so forth. What's really interesting actually about this graph is that if we switch the graph to just plt.plot instead of plt.scatter, and we run it, notice it's actually the exact same thing. However, with the linear plot, we're basically just playing connect the dots with all the points, whereas with a scatter plot, we're just showing the actual points themselves like this, if that makes sense. So this is how you do a scatter plot, pretty much the same as a linear plot, just writing scatter instead. And scatter plots are actually something we're going to look at a lot in future videos because they're very, very useful for something that we call correlation, which we'll look at starting in the next episode. Now, the next type of graph I want to go over using this library is a bar graph. So bar graphs are a simple method of data visualization that give the total count of a series of variables. Let's actually go down to this new code chunk down here, And I want to go ahead and just make my own list to give you an idea of how bar graphs can work. For bar graphs, we need two primary arguments, the labels and the actual values themselves. So let's make a variable for each one of those. I'm going to make a variable. I'm just going to call it labels. I want to make it a list. I'm just going to pass in like A, B, C, and D for right now. And then for our actual values, let's make another list called values. I'm going to set it equal to, let's say 10, 20, 30, and 40. And then to actually plot this graph, we can just go down here and we can just type plt.bar. And then what we're going to do is pass in our labels first and then our values second. And then just like last time, we can write plt.show at the bottom of this block to explicitly have the code show us the graph. So we want to make sure when we're doing a bar graph that we're always passing in the labels argument first, because it has to be in that order. The labels have to be the first one and then the values have to be the second argument. So now if we go ahead and just run this code, you'll see it now prints out a super basic bar graph that has 4 points of data. And notice how the ordering of the labels and values actually matters, because the order determines what gets assigned to what. So for example, the first label here is A, so A gets assigned to 10. B is the second one here, gets assigned to 20, C gets assigned to 30, D gets assigned to 40, and so forth. And this becomes important when working with actual data sets because we want to make sure our data has the correct labeling. And then in the same way we did this with our previous graphs, we can change the axis labels. So let's just add in some lines here. I'll say plt.xlabel, and then I'll just pass in, I'll say label axis. And then I'll do plt.ylabel, and I'll just have this as the value axis. And then we can actually add a title to our graph as well. I'm going to make something down here. I'm going to call it plt.title, and then we're just going to pass in, let's just say, graph title like this. And then now if we actually run this, you'll see it now has a title, just called graph title, then the value axis, and then the label axis. And also, just like the previous graphs, we can add some customization things to the graph if we want. So let's add some colors here. Let's just add a new list here. I'm going to call it colors. And then let's just make a list of just some well-known colors. Let's say red for one. Then we'll have green, blue, and then let's just say purple. Now, we can then pass in this list to the actual bar function to get it to plot the colors. So to do that, all we need to do next to here is make a comma for a third argument and write color equals, and then we're setting equal to this list we made here, which is just colors. So we're just saying color equals colors. And then if we run this code chunk here, you'll see it now makes our graph colored based on the color list we made, and also in the exact same order we pass it in. So the first one is red, second one is green, third one is blue, fourth one is purple. Another super quick customization thing we could do to change this bar function would be to change it to bar H instead of just bar, which just means horizontal bar function. So if I just change this to bar H instead of bar like this, and I run it, it just flips the axes to make the bar graph horizontal as opposed to vertical. Now the only thing that if we were to do this, we should note is that we need to swap our labels around, because now you can see that on the y-axis we have value axis, on the x-axis we have label axis, where actually it should be the other way around to match it. So if we're going to switch it to horizontal, we got to flip our axes as well. So let's change this to y label and then x label. Then if you run it like this, you'll see it now has the correct axes labels. Okay, so one more graph I want to go over before we get into our actual data graphing is the idea of a histogram. So histograms are a super common type of graph that are used to show the numerical distribution of data points over given intervals. That may sound kind of complicated, but it's actually very useful as a graph and not very hard to actually implement. So for our model data, let's just create a bunch of random data points. To do this, I'm going to use the Numpy library, which is a super helpful library that is used in all sorts of computing and Python, and adds tons of helpful functions that we'll go over more in future videos. For now, though, let's actually just import that library in this block. So I'm going to say import NumPy as np, and this is how I'll access this library. So I'll just go ahead and just run this real quick, just so we have it. So I'm going to try and just generate a random set of numbers here. So let's make a new variable. I'm going to call it data point and set it equal to np, which is just NumPy that we just imported, .random, .normal. And then I'm going to pass the numbers in, and I'll explain exactly what they mean here. So what this basically does here, this just generates a normal distribution of data points where the first number is the number it's centered around, so they're all going to be around 100. The second number is the standard deviation, and the third number is the amount of data points we're actually generating. So if we now print this out, let's just print data points, and we run it, you can see that we've now actually printed 100 data points that are all somewhat in the ballpark of 100. So now let's use these to actually show you what a histogram looks like. So I'm going to go ahead and delete this print here, and then I'm going to make a histogram. To do that, all we need to do is type plt.hist, and then we're going to pass in the data points that we have. If you're starting to pick up on the pattern, you can tell that whenever we're using material plotting library or PLT, to do a type of graph, you generally just are going to type the abbreviation of the graph name. So like histogram is just hist, bar is just bar, obviously, and then you have like scatterplot is just scatter, and so forth. So that's kind of the general pattern that it follows. So let's go to the bottom. Let's type plt.show like this. And then if we run it, you can see that it's now printed off a histogram here. So basically how you read a histogram is you look at the bottom axis to find the ranges. And then the blue bars determine the frequency of entries in each range. So for example, it looks like our ranges are in increments of 5 if you just look at the width of the blue bars. So this first one on the very left around 70, looks like it goes from about 70 to 75. And then we look at like the one from 80, goes to 80, 85, and then 85 to 90, and somewhere in that range. So basically for each range, you can look at the height of the bar to see how many data points fall within that range. So just to kind of give you an example, if you look at this first one here with like that's around 70 to 75, looks like there's probably, it's probably too tall, like according to the y-axis, so it's probably 2 entries in that range. If you look at the 80 to 85 one, I'd say maybe 7 or 8. 85 to 90 would be right around 5, and so forth. A normal distribution is one that follows somewhat in this shape, basically where it tapers off kind of at each end, and then has many entries located right near the middle. Hence why we use the normal function up here like this, because that makes a normal distribution. So I could sit here all day and demonstrate all different types of graphs with material plotting library, but there's so many different types that it would actually just take forever. However, once you get familiar with plotting one or a few, the rest will actually follow pretty easily, as the process is pretty much identical in all of them. It's just the fact of you're calling a different name on each one. So make sure you have your data points or labels ready, and then you just find which material plotting library function you want to use, call the function on your PLT object, and then pass in the data points or labels. So now that we have a solid understanding of how to make some basic bar graphs in material plotting library using just fake data that we made, let's actually implement the data from the dataset we've been working with in our AI Global Index. Let's now implement what we learned with a basic line graph to model some data from our dataset. One thing that line graphs are effective at is seeing the correlation between two variables. So for example, if we go ahead and scroll up here and look at our actual dataset, what if we look at this data set and we looked at the total score variable here, and then we were wondering which of these variables is basically the best predictor of the total score variable? If we wanted to know this, we could just put total score as our dependent variable, and then just try out multiple of these variables like talent or infrastructure or operating environment as our independent variables. And then if any of the graphs look somewhat like a one-to-one line or like a y equals x line, we could possibly conclude that there is a strong correlation. So that would mean a line that looks something like this, where it kind of goes straight up diagonally, meaning they're positively correlated. So let's do just that. So let's go actually down to this code block down here, and I'm going to make an x variable and a y variable that is equal to each axis, just like we did with the model data. So to set these variables, we can use what we learned about data selection in our selection episode. So let's first set our y variable, which will be our dependent variable, to total score. So to do that, let's just write dataset, and then we're going to select total score like this. And then for this graph, we wanted to cycle through some of our variables for our x variable to see if there's any apparent correlation between any of them. In our dataset, every one of the variables like talent, research, operating environment, etc., culminates to make the total score, so there will likely be some degree of correlation in all of them. But we can look and see which one has the strongest degree of correlation. So just to start off, let's just select, for instance, let's say the talent variable. So let's make our x variable equal to dataset, and then we'll select talent. And then we'll use what we learned with graph creation to basically plot this with PLT. So we'll say plt.plot and then x and y. And then real quick, I want to make axis labels before we print it out. So I'm going to say plt y label is total score. And then we could say like plt x label is equal to let's see, talents. And then we'll just say plt.title is total score versus talents. I'll separate that a little bit to make it look a little cleaner. And then I'll write plt.show at the very bottom. And then if we run this graph, oh, oops, I mistyped that. It should be plot, not plt. So then if we run this, the graph will look something like this. So we have our x-axis, which is our talent column, and our y-axis, which is our total score column. Because there's not many data points in this data set, the line is looking rather jagged, but does appear to be positively correlated to some degree, meaning that as our independent variable talent increases, the dependent variable total score tends to increase as well. Looks like there are definitely a few exceptions, particularly the jagged point right around 20 for talent and 60 for total score, but it is generally trending positively upwards. So next, let's take a look at another variable for our x variable. And actually, just to make a quick upgrade to this, instead of having to change like all the labels and stuff, we can actually just do something like this. I'm going to say xvar equals like talent, and then instead of having to retype it, I can just pass it in this variable here. So I'll say like xvar like this, and then I will say xvar like this. And then let's just pass that into the title as well. I think this should work. Let me try this real quick. I'll type in xvar like this. Let's see if it gives me... okay, it might get mad that I'm doing that. Let me try it this way instead. Xvar like that. Okay, there we go. So yeah, that works. I'll go ahead and space this out. Basically, the idea of what we did there is just if we want to change the X variable to look at different variables, we don't have to actually change it in every single field. So now if we wanted to change it to something like, let's say, infrastructure, we could run it like that, and it would change the actual variable itself, plus the axis label, plus the title label. Once it's run, you can actually see that this line graph seems to be pretty jagged as well, and possibly a little bit less correlated with total score than talent was. There's definitely still a positive trend in the upwards direction, however, it's much more jagged in the middle and has a few more outliers. Let's look at another one, say operating environments. Let's change the X variable here to just equal, we'll say operating environment. I think it's lowercase like that. Run it here. Okay, maybe it's not lowercase. Environment. There we go. So it looks like this graph is probably even worse than the last one. It's really jagged, meaning there's a lot of deviation. There's still obviously a trend upwards. However, it's weaker than the previous two, and operating environment doesn't really seem to be as heavily correlated to the total score. Let's look at one last variable. Let's look at research. So I'm going to change this to research instead. And then I'm going to go ahead and run it. And voila, this graph actually looks a lot better than our previous graphs and probably the best one yet. As you can see from this graph, it looks almost perfectly diagonal, minus obviously there's a few jagged edges towards the beginning, which says to us that generally, as research increases, total score tends to increase as well. In the same vein, as research decreases, total score tends to decrease as well. We could do this for a while for each variable, but you basically should get the gist of it now. If you want to use a line graph, you typically select two columns from within a dataset and plug them into a material plotting library, and the resulting graph can tell you a lot about the correlation between two variables of data. What if, however, we don't like how this linear plot really looks? Frankly, the line being super jagged looks kind of ugly, and it's definitely not the cleanest way we could show correlation. When we have a bunch of point like this, it's going to be better to use scatter plots instead of line plots so we don't have all these jagged lines. So all I'm going to do is actually just copy and paste, or actually copy all this thing here. I'm going to go into this code chunk here where we have the scatter plot. I'm going to paste it all in like this. And instead of having plt.plot, all I'm going to do is just change this to plt.scatter. And then now if I run this, you can see it actually looks a lot better. Now we just have the values themselves instead of having a million different little lines connecting them and making the graph look a little polluted and dirty. Again, we could easily change this X variable to something like operating environment. So I could do operating environment and then run it. And it would look something like this. This is not very correlated. It looks like it's kind of ugly. And then I can go, just change it again. Look at infrastructure this time. I'll go infrastructure. A little better. Let's do what we did last time. I'll go talent again. Basically, all I'm doing is the same thing as the line graph. I'm just swapping out different X variables. And again, I'm just using a variable here that I can just change once so I can plug it into the X label itself, plus anytime I'm actually like labeling it on the actual axis or the title. And again, scatter plots like this are actually super, super helpful for looking at correlation, much better than line graphs in my opinion. And we're actually going to be using them a lot in our future episodes. So make sure you just know how to do a simple scatter plot, but it's pretty easy. All you need to do is have a X column and a Y column, and then call plt.scatter, and then pass in X and Y as the two arguments. Next, let's move on to using bar graphs with real data. So let's actually go back up to our data here, and let's think about how we could use a bar graph for our data. It wouldn't really make much sense to do like a frequency counting kind of thing with our numerical data, because that's what histograms are good for. Instead, we could just find the total frequency for each possible answer in one of our categorical variables, like region, cluster, income group, or political regime, and then plot it using a couple of bars. So actually, for instance, let's take the column income group, for instance, and within income group, we'll find the total count of each answer. So basically how many countries are in each income group. So to do that, we can actually use a really simple function in Pandas called value counts. So I'm actually going to go back down here. And then I'm going to call a function. I'm going to say dataset dot value counts, and then we're going to pass in the column we're looking at. And then if I go ahead and just run this line here, you'll see that it prints out the counts of each income group. So there are 43 incomes that are high, 10 that are lower middle, and 9 that are upper middle. So we know from looking at our bar chart earlier that we need to have labels as well as values, and we're going to pass in labels first and the values second. And there's a super simple way to get our labels. So let's make our actual value counts into a variable to basically just capture the output. So I'm just going to name it like income counts and set it equal to what we just made. And then to get our labels, all we need to do is make a variable that's just called labels. And then we're going to set it equal to list income counts.index. So basically what this is whenever we run the value counts function, it returns what's called a series in Pandas. And to access the names, we need to use the index attribute, hence why we're calling income counts.index. And then we're wrapping this all in a list because we want to convert the whole thing to a list so we can plug it into our graph. And then to make our values, it's pretty simple. We'll just say values, and then we're going to do list as well, and then just make it our income counts thing here. If we access the income counts directly, it'll look at the values, and you want to turn that into a list as well. So now let's actually make our graph. So let's go down here. I'm going to type plt.bar, and just like last time, we're going to pass in our labels first and our values second. So I'm going to pass in labels and then values like this, and then I'm going to type in plt.show down here. So then if I go ahead and run this now, you'll see it gives us a nice bar graph that details the frequency of each income group. Of course, this graph corresponds directly to our value counts function. So high has a count of 43, lower has a count, lower middle has a count of 10, and upper middle has a count of 9. So now let's make some helpful labels just to help us look at this graph a little better. Right here, I'll add plt.x label. We'll say income group, and then I'll make plt.y label. I'll just say count, because that's what we're counting. And then I'll make a title. I'll just say plt.title, and then we're going to say counts of each income group. And then if we run this, you see we have a very nice example of a simple bar graph that is labeled and counts the frequency of each categorical variable in the income group. And just like with our example bar graph, we can change the colors if we want to make a colors list. So let's actually go down here. Let's make a colors list. Let's just say, make a list here. I'll just say green. Let's do green, red, and blue. Green, red, and blue like that. And then now, forgot to pass it in. Do color equals colors. And then now if I run it, you see that it has nice color variation now. And also like the previous one, we can change this to bar H if we wanted to turn this into a horizontal bar graph. So I could do something like this. And it would change it horizontal. I would just need to make sure to switch the axes around if I did that, like this. Next, let's look at implementing a histogram using our actual data. This one will actually be the simplest of all the graphs we've looked at so far. So to make a histogram, all we need to do is grab a single column of numerical data to check the frequency spread on that column. Let's look at perhaps the most valuable numerical column in the whole data set, which is our total score variable. So let's make a variable called values. I'm just going to set it equal to the total score column. So I'm going to say dataset total score like this. And now that we have the column, the only thing we need to do is to make a histogram is to pass in our dataset here, our column here, values, into plt.hist function. So to do that, all we need to do is type plt.hist. I'm just going to pass in values here, and then I will type plt.show. And then now if we run this, you'll see we now have a histogram of our data. We have two outliers kind of here on the right-hand side. We have one near 100 and one near 60, which if we actually look back at our data set, we can see that those are the US and China. However, most of these fall kind of in the 0 to 50 range, which can be seen if we just look at our data set in tabular format. You can see if we just go up here, obviously we don't have all of them printed off, and these are the top ones, but we have the two outliers here, US and China, and then the rest are going to fall, that's development. US and China here, and then the rest are going to fall, kind of 0 to 50 or 0 to 40 in the range below that. So I'll go ahead and just scroll back down here just so we can see it again, and you can see it reflects the table pretty well. So what this histogram basically does is help us better visualize the distribution of all total scores within this index. So similar to all of our other graphs, let's make some helpful axes labels and a helpful title. So I'll just do plt.x label. Let's say this will be total score. Oops, I can't type. And I'll say plt.y label. I'll do frequency. And then we'll have a title. Let's just say frequency of all total scores. And then if we print it off, we have a really nice histogram that gives us the frequency distribution for the total score column, obviously now with labels. If we wanted to change the variable that we're looking at, all we'd have to do is change the column we're selecting. So for example, we could replace total score with research here, like this. And obviously I need to change the labels too, although for now I'll just run it just so you can see. And we get a different histogram entirely. If we run it, you see this histogram is a bit less balanced than our previous one, as it's a lot more right skewed, with most of the entries occurring on the left-hand side of the graph. Hopefully now you should have a solid understanding of how to make line graphs, bar graphs, histograms, and scatter plots in Material Plotting Library. I wish I could go over every single type of graph in this video, but Material Plotting Library has so many graphs that it would take forever to get through all of them. However, now that you have a basic understanding of how graphing and visualization works with Material Plotting Library, you should be able to use their graphs in the future with some moderate adjustments. I'll post the link to Material Plotting Library in the description, and with that, you'll be able to access every single function in the library and see what all different types of graphs they have. If you want to make more advanced visualizations, you can use a library called Seaborn, which is actually based off of Material Plotting Library. For now, though, you can take the knowledge you've made with Material Plotting Library to get yourself started on the right track. In the next video, we'll go over some concepts of statistical analysis and really dig into some of the analytical aspects of this course. I'll see you in the next one. Hey everyone, and welcome back to our Python data analytics series. In the last episode, we went over data visualization. In this episode, we're going to go over some common analysis functions and explore the idea of correlation. So this will involve getting things like mean, median, and standard deviation, as well as finding correlations between two variables. So the first thing I actually want to do is quickly do a review of some stats terms so we're all on the same page here, since we'll be using functions to find these terms very shortly. This isn't a stats course, so I'm not going to go over these terms incredibly in depth, but we should all at least know what they are. So the first term is mean, which just means average. A mean is acquired by taking a set of numbers, adding them all up, and then dividing them by the total number of numbers that there were, and then that gives you the mean there. So if we had this list here, we add them all up, this list here, we add them all up, we get 350. There were 5 total numbers, we divide it by 5, we get 70, so 70 is our mean. So next we'll look at the median. So median is just the middle number in a set of numbers when they're sorted in order. So let's say we have 5 numbers, we have 40, 10, 28, 7, and 85. So to find the median, we first need to sort the numbers, so we'll just write them as 7, 10, 28, 40, and 85. And then if we look at the middle entry in this series, it is 28. If we, for instance, were to take out the 28 and we had a set of even numbers, then the median would just be the mean of the two middle entries. So in this case, it would be the mean between 10 and 40, which would just be 25 in this case. Next, we'll look at the variance. The variance is the mean squared difference of each data point measured by the mean. What this means is that we find the mean, then we find the difference of each value in the data set from the mean, square it, and then add all these together and then find the mean of these numbers. If that sounds kind of confusing, let's look at a really simple example. Let's say we have the numbers 2, 3, 7, 9, and 12. So we first need to find the mean of these numbers. So to do that, we're going to add all these numbers up, which gives us 33, and then we divide it by 5 total numbers, which gives us a mean value of 6.6. And then for all numbers in our list, we need to find how far away each number is from the mean and then square it. So to do this, we can just use subtraction. So the very first number we have on our list here is 2. So let's just show an example of how we'd find the square difference of this number. So we would take 2 minus the mean that we calculated, which is 6.6. And then this should come out to be, I believe, negative 4.6. And then we square it, which becomes 21.16. And then we would repeat this process for every single entry. So we do the same thing for 3, 7, 9, and then 12. And so that's why you see these numbers here. We have 12.96 for 3, 0.16 for 7, 5.76 for 9, and 29.16 for 12. Then we just want to add them all together and divide them by 5 total entries, which gives us 13.84, meaning our variance is 13.84. So variance squares the differences to avoid negative numbers and just gets absolute value differences. However, this should be noted when we look at our final variance value of 13.84. This value is the mean of all the squared differences. So if we want to get our variance number back down to normal units instead of squared units, we should take the square root of that. If we take the square root of 13.84, we get 3.72. But guess what? Now we've just found our standard deviation, because standard deviation is just the square root of variance. So our variance is 13.84, and our standard deviation is just the square root of that, which is just 3.72. So standard deviation is basically just measuring the average deviation from the mean that each value has. So basically, it is measuring how dispersed and varied the values actually are. So hopefully now, after that really quick review, you should have a refresher or base knowledge of what all these statistical terms actually mean. So let's actually apply them to the data set we've been working with to get started with our statistical analysis. Now, Pandas actually has super easy functions for every one of these terms we just went over, meaning we don't have to sit here forever with our calculators trying to figure out what these terms mean. Pandas can do it in one line for us. So let's take mean, for example. Assuming we have our AI data set loaded in, let's call this mean function. It's literally just as easy as typing mean. So I will type datasets.mean like this as a function. And then if I were to run this code block, you'll see that it prints off the mean value for every single variable in the table. This mean function treats each numerical column as a set of numbers and then performs mean calculations on every single one of them. So after summing up all the talent numbers in our data set and dividing them by the number of entries, the mean is 16.803, for instance, as we see right here in the table. Doing the same for infrastructure, we can see that the mean is 63.5. This mean function is basically called on the whole data set and will print out this really nice, simple tabular format for each variable, which could help tremendously in your overall analysis. So if you actually notice here, we're getting a little warning that says, there's a numeric only thing here. And if you read it, basically what it's saying is that it's giving us a problem because we're selecting the entire data set, which is technically an issue because we have columns that are non-numerical, like income group, that don't have numbers in them. So to silence this warning or just to select whatever columns we want, we can use lock or iLock functions from the data selection episode to select specific columns to take the mean of. So what I mean by that is doing something like this. Let's use our log function to actually just select all the numerical columns we have. So I'm going to use colon for the rows to select every single row. Then I'm going to select only the numerical columns, which is everything from talent all the way through total score. And then now if we run this code, it prints off the same exact thing as before, except the warning is removed since we're specifying the exact columns we want to look at, which are just numerical. And of course, as with anything else with our selection, we could narrow it down if we wanted to. Let's say we only wanted to grab all the columns from, let's say, talent to research. We could just replace it like that, print it off, and then it only grabs the mean for these 4 columns. So talent, infrastructure, operating environment, and research. And as usual with lock, we can do really any selection we want. But of course, we wouldn't need to use lock if we wanted to just select like columns individually by hand, whether we just grab like 1 or more. So if we want to look at the mean of like just talent and total score, we could actually just remove the lock here. And then what we could do is just remove this colon here. And then we could do something like this, except we would need double square brackets here because it's technically a list inside of this. And then if we did it like this, we would just be selecting the talent and research columns without actually having to use the lock function. So if we were to run this, you see it only prints off the mean for talent and research. And of course, if we wanted to, we could just select more columns. Like obviously, we can just put it like total score or something like that here, and it would have the mean of total score as well. And lastly, we could just grab the mean of 1 column if we wanted to. So I could just remove this list here, and I could literally just pass in a string of a single column like that and say, what is the mean of the talent column? We print it off, it is 16.803. So just a minute ago, we went over these other terms besides mean, like median, variance, and standard deviation. And one of the great things about Pandas is that every single one of these terms has a super easy function to grab them to. So let's get new code chunks for each one, which I have down here. So to grab the median of the whole data set, we can just type dataset.median like this, and then it will give us the median value of every column in the data set. If we wanted to grab the variance of the entire data set, we could say dataset.var like this, and it will give us the variance of every single column. And then to grab the standard deviation of all the entire data set and all the columns, we could do dataset.std like that, run it, and this gives us the standard deviation of all the columns. So just so we're all on the same page, let's go up to median real quick, which we just calculated. And just like we went over with the sample data, this function will look at every column and find the middle value when they are sorted properly. So the middle value or median for, let's say, the development column is equal to 9.005. And this is the same case for obviously every other column. We sort them in order, look at the middle entry, and then we can calculate the median for every single one of these columns. And the same selection rules are going to apply with median. Like for instance, if we wanted to grab the, let's say the research column's median, obviously we could just type in research like this, and it'll give us just the median of the research column. And then if we look at the variance here, we need to calculate the mean of the squared differences of every value from the mean of each column. So in doing that on an entire data set by hand would take forever. So luckily Pandas does it all for us. So for example, the average squared difference or variance of every value in the government strategy column is equal to 689.19. And then we know the standard deviation is just the square root of variance. So for example, 15.21 standard deviation for talent is just the square root of this 231.49 number up here. And the same applies for each one of the values on this list as well. They're all just square roots of their corresponding variance numbers. So just so we can get a little bit more comfortable with the idea of selection using these functions, let's actually just go up here to our median. And let's say I want to find the median of all columns between talent and development. So to do that, I could do something like this. I could say .lock. I would select every single row, and then we want to select every column all the way from talent all the way to development, and then run it. And I would get the median of these 5 columns. Next, let's say I'm looking for the variance of the columns talent, research, and total score. We could do it something like this. I could do double brackets here, and I could just pass it in as a list. I can say talent, research, and then total score like that. And then if we run it, it would print off just the variance of these 3 columns. Lastly, let's just say I want to find the standard deviation of just the government strategy column. To do that, I could just do a simple square bracket here. I could type government strategy like this, .std. If I run it, it will give me the number of standard deviation for the government strategy. So basically the idea that I'm kind of getting at here is that you can use any of these mean, median, variance, or std functions with any possible selection of data. This can be a super helpful part of statistical analysis as mean, median, variance, and standard deviation are 4 super common measurements of data sets. So the last thing I want to do in this kind of shorter episode is look at something that is super common for data analysts to actually explore, and that's the idea of correlation. One of the most common things data analysts or data scientists do is explore the data to see if one variable strongly affects another, or basically seeing the relationship or correlation between two or more variables. One way to check correlation would be to make individual plots in the same way that we did in the data visualization episode, using something like scatter plots. So when we did this, we just used material plotting library to plot two individual columns from our dataset to try and look at the correlation between that. If you wanted to do that, you could of course go that route. However, there's a much faster and more efficient way to look at the correlation to do this. So in the very last episode, I mentioned a library called Seaborn that basically builds on top of material plotting library to build better graphs. And in this episode, we're going to use some of their functions to help us out. So Seaborn has a function called pairplot that actually looks at every single variable in the dataset and plots every possible graph between two variables. Let's actually use this function now to see what it does. So the first thing I'm going to do is actually import the Seaborn library. I'm going to say import Seaborn, and then I'm going to import it as SNS, as SNS is typically the abbreviation you'll see used for Seaborn in code. Then all we're going to do is just type sns.pairplots, and then we're going to pass in our data set. So if we run this, it'll take a minute to actually print it out because it's looking at every single variable and every single row, so the overhead computing is quite high. I'll go ahead and fast forward this here so you don't need to wait for all this to load. And voila, we now have a huge grid of graphs. It might just look like a blob of dots right now, but here's how this pairplot function actually works. So basically what it does is it plots every single variable once on the y-axis. So if you see here, we have on this y-axis here, we have talent, infrastructure, operating environment, research, and so forth. And then it also plots it once on the x-axis, so down here as well. So we have talent, infrastructure, operating environment, and so on. So what it does is it pairs every single variable up until every variable has been paired with something else. So basically there is a graph in here that'll have, let's say, talent on the y-axis and research on the x-axis. Just like there's one that would have research on the y-axis and talent on the x-axis, there's one that would have, let's say, development on the y-axis and total score on the x-axis. So it's basically every possible combination of two variables on this graph. So if, for instance, we need to look at the correlation between operating environment and research, we would find the operating environment on one of the axes, so we could look at this y-axis here, and then we would find where it intersects with research on the other axis. So let's actually scroll down here. Looks like research is this fourth column here. So if we scroll back up, it looks like this graph right here is a correlation between operating environment and research. So because operating environment is on our y-axis, that means it'll be our dependent variable, and because research is on our x-axis for this one, that would be our independent variable. So because of the way this pairplot function actually works, each combination of two variables has a mirrored graph where the axes are just flipped. So if there is a graph where operating environment is the y-axis and research is the x-axis, there also exists a graph where operating environment is the x-axis and research is the y-axis. So for example, look at like these two graphs here across this diagonal. If you look here, you can actually see that these are actually two perfectly mirrored graphs of each other because they actually involve the exact same variables. They're just kind of on the flipped axes. In the same way, if you look at these two graphs here, these are also mirrored because this one has research on the y-axis and then operating environment on the x-axis, whereas this one right across from it diagonally has operating environment on the y-axis and then it has research on the x-axis. So now, what are we actually looking for when looking for a strong correlation? The most common case of correlation is going to be a linear correlation, as this is common and easy to identify. So all that we look for in a linear correlation is a diagonal trend upward or downward. An upward diagonal trend would suggest a positive correlation, while a downward diagonal trend would suggest a negative correlation. Positive just means that the two variables move together, while negative just means the two variables move opposite of each other. So in this grid, most of these variables have some degree of correlation, whether very strong or very weak. So real quick, let's take a look at our grid and see if there's any graphs that stand out as having a somewhat tight diagonal linear correlation. If we look, for instance, let's see, one that sticks out to me right away is this one right here. It looks like with the research on the y-axis and it's talent on the x-axis. So it's this graph right here. This one looks to be like it's pretty nicely correlated. Let's go, okay, total score and talent also seems to be a very good one, where it follows kind of a nice upward diagonal trend. And then another one, which looks maybe even better than that one, is the one that has total score on the y-axis and research on the x-axis. This one actually does look pretty good too. It looks like it's a very tight diagonal correlation there. So why do all these three graphs really stand out to me? If I were to place a perfectly straight diagonal line starting somewhere near the bottom left of the graph and it went perfectly to the top right, many of the data points would fall around that line. So if we go up, like let's say between research and talent, for instance, this graph here, what this means is that generally, as the research score goes higher, the talent score tends to go higher as well. In the same way, as the resource score goes lower, the talent score tends to go lower as well. Because the variables tend to move together, we would say research and talent are positively correlated. And then the other ones where we found kind of a tight diagonal was, for instance, this total score and this talent one here. This one represents the same positive correlation, meaning total score and talent tend to move very much together. And then, however, it looks like the strongest correlation that we can actually find in this whole grid comes from this graph here that I'm looking at, with total score on the y-axis and research on the x-axis. This graph has data points that follow a far tighter pattern than any other graph on this list, and it appears that total score and research have an incredibly strong correlation. And not only are almost all data points in the lower ranges tightly clumped together, almost 1-to-1, but also if we look at these two outlying dots here in the higher ranges, they look like they're actually still quite in line with the diagonal produced by the lower ranges, meaning that if I made a line here with these lower ranges, and I made a diagonal to kind of go in the middle of all of them, that if it actually kept going, it looks like these two dots would actually be fairly in line with that. Just so we can see this a little bit better, let's use what we learned about material plotting library to further explore this correlation. So I'm going to make a new code block down here, and I'm going to make a scatter plot to actually explore this. So I'm going to type plt.scatter, and then we're just going to pass in the columns of total score and research to make this graph by itself. And remember, we always want the x variable to be first. And so this graph here, we have research as the x-axis variable. So I'm going to pass in datasets research, and then separate by commas to pass in the columns argument. So I'll say datasets total score like this. And then, then I'll actually add plt.show to the bottom of this. And then if we run it, we've now recreated this exact total score and research graph by itself. So this graph here is perfectly identical to this graph here. Obviously, we're just doing this one individually though. And like normal, let's make some quick labels just so we can be a little bit neater about this. Let's say plt.xlabel, or call it research. Then we'll do plt.ylabel, call that total score. And then we'll do plt.title, and then we'll just say total score versus research, like that. And then we'll just run it to have a nicer formatted graph. So now you should have a better idea of what this graph looks like up close. If I were to place a line on this graph to follow the general trend of the data points, we could probably get a very accurate linear correlation between these two variables. Meaning if I had a line starting somewhere in this area and I went all the way perfectly diagonal, all these points would fall somewhat around that line. So the real question is though, how do we actually find that line? Or more importantly, how do we find the mathematical equation for the line given our data points? We'll explore that in our very next episode where we cover predictive analysis with things like linear regressions that are meant to help us find these prediction values. In this video, you learned how to use all the mean, median, variance, and standard deviation functions, as well as finding the correlation between two variables easily using the pair plot function from Seaborn. And as promised, in the next one, we'll look at finding trend lines for linear correlations and further explore the idea of data prediction. I'll see you in the next one. Hey everyone, and welcome back to our Python data analytics series. In this video, we're going to go over some simple predictive analysis using simple linear regressions and multiple linear regressions, as well as plotting these predictions and checking their accuracy. In our last video, we left off by looking at the correlation between research and total score. To further explore the idea of correlation, we should build a predictive model that is able to predict some value based on another value, to truly test whether our data is correlated or not. One of the most common ways to do this is by making what's called a linear regression. Before we get into the coding, I want to quickly go over what a linear regression is and how we're going to actually use it. So, as we know, any straight line in two-dimensional space can be graphed by this equation, y equals mx plus b. And basically in this equation, y is the y-coordinate, x is the x-coordinate, m is the slope of the line, and then b is the y-intercept of the line. So let's look at an example real quick just so we can go through this. So in this graph here, we have a line that is equal to y equals 5x plus 2, and it looks like this on the graph. The idea is, for any value of x that we plug in, we would get a corresponding y value. So if we plugged in, let's say 2 for instance, into this equation, let's say we plug in x equals 2 to this, we have 5 times 2 is 10, plus 2 is 12, so y should be equal to 12 when x is equal to 2. And we can actually see that if we go and look at our graph here. If we look at this coordinate right up here, it looks like right where x is equal to 2, y is equal to 12. So basically, in this y equals 5x plus 2 equation, x and y represent any possible x or y coordinates, 5 is our slope, and 2 is our y-intercept, and you can see the intercept here, right at 2, because that is where the x-coordinate is equal to 0, and where it crosses the y-axis. So, using what we now know about lines, let's make a definition for a linear regression. So, a linear regression is basically just a technique for predictive analysis, and it uses what we know about lines on a graph to estimate future values given old values. So the idea is basically that if we have a scatter plot that has tons of different dots that represents a wide array of data points, kind of like this one with total score versus research, we should be able to find a line that fits and approximate all these data points and minimizes the variance from the points, meaning most data points will fall around this line. If you notice here, if you look at these scatter points here, you can see that it definitely does follow an upward diagonal trend. So the idea of a linear regression is basically finding the line that actually matches this trend the best. And the idea is that if I were to make this line start near the bottom and then go all the way to infinity, a good model would have points still following the trend of this line. So this is all that a linear regression actually is. Basically a technique to find a line that best fits the data. If the model is good and the line approximates the data really well, we can conclude that two or more variables may be heavily correlated and can even use it to predict future values. So then how would a linear regression work mathematically then? So basically all we need to do to find a linear regression is to find the slope that we need, or our m value, and then find the y-intercept that we need, or our b value. Luckily in Python, we don't need to actually do any of these calculations by hand, as Python will do it completely for us, although we do need to know the commands to execute it. An equation like this that's just using y equals mx plus b on a dataset would be called a simple linear regression because we're just looking at two variables, x and y, where y is our dependent variable and x is our independent variable. However, we could add more x variables and coefficients to this equation, and it would mean that we're feeding in multiple different variables to predict a single variable. And this is what's called a multiple linear regression if we were to do multiple variables in that fashion. So if we wanted to actually look at this in the context of the data set that we're using, how would we select our variables and how would we figure out our simple linear regression line? Well, right here we're looking at the correlation between total score and research. So if we wanted a simple linear regression for this graph, we could have research as our x variable or independent variable, and then have total score as our y variable or dependent variable. In doing this, we would see the correlation between research and total score and model if research does truly affect total score that much. If we wanted to do a multiple linear regression, we could have research, talent, and commercial, for instance, all as our x variables, so having multiple variables, and maintain total score as just our y variable. So let's actually move on to our code now so we can try this out, and you can see what I mean. Okay, so the library we're going to be using for this is called sklearn, and it's one of the most common libraries you may see for data science or machine learning, and especially predictive modeling. So to import, let's just go in this code block down here, and I'm just going to write from sklearn import. I'm going to import two modules basically, an import model selection, and then also linear model, just as we would import any other library module. Another library we want to import, which happens to be one of the most popular in Python, is Numpy, and I'll explain why in just a moment. So for instance, just now, I'll just write imports numpy as np like that, and then I'll just go ahead and run it just so we have it. Okay, so let's start with our simple linear regressions now. We found up here with our correlation graph that the best single variable to try and isolate and correlate with total score would likely be research. So let's actually go and declare variables for our simple linear regression. So I just want to set x equal to our research column. So I'm going to say x equals datasets research, and then I'm going to say y equals datasets total score like this. However, there's one modification we need to make to this before we go on. So by default, when we select a column like this, Pandas stores it as a one-dimensional data frame. However, the sklearn library we're going to be using doesn't accept this format, so this is where Numpy actually comes in. So to use the sklearn library, we'll want to turn this data frame into a Numpy array instead. So to do this around both these variables here, I just want to wrap it in np.array because np is our Numpy object. So I'm going to say np.array, wrap this whole thing in that, and I'll do the same exact thing for our y variable as well. And one final thing before we can go on. By default, lists or arrays are a singular row of data. However, in our model, we want to look at one singular column, not a row, so we need to change the shape of the array to be vertical rather than horizontal. And luckily, Numpy has a thing for this. So to do this, we can use Numpy's reshape function to the end of these lines here. So inside, we specify the shape that we actually want. So what I'm going to do is I'm going to type reshape like this, and I'm just going to put -1 and 1. So basically what this argument means is when we're using reshape, the first argument is in reference to the rows, and the second argument is in reference to the columns. If you put a number here that's like 1, 2, 3, 4, 5, whatever, that specifies the number of either rows or columns that you want. And if you put -1 in here, it'll actually fit the other one just to match whatever the other shape is. So basically what I'm doing here is I'm specifying we want one column, and then we're just going to fit the rows to match whatever our columns need. So I'll go ahead and do that same thing for our y variable too. I'll just type reshape -1 and 1 like that. Now that I've correctly shaped these variables as Numpy arrays, we can move forward with our simple linear regression. One very important aspect of linear regression and just predictive models in general is that we should always have a training set and a testing set. The training set will be used to actually train our model, and then the testing set will be used to test the accuracy of our model and see if it gets things right or not. If we didn't split it up and we used the exact same data for our training and testing set, our model would get 100% accuracy because we're feeding it the exact same data, which wouldn't make a whole lot of sense. So in this next line, I'm actually going to make our training and testing sets, and it's going to be kind of a long string of words, and it may look really confusing at first, but I'll break it down step by step. So I'm just going to go ahead and write xtrain, xtest, ytrain, ytest, and then I'm going to set it equal to model selection that we imported from our sklearn library. And then from that, I'm going to call the train test split method. And then I'm going to pass in 3 arguments, our x column, our y column. I'm going to set an argument of test size equal to 0.2. So what does this line mean? Let's first look at the right side of this equation and see what's actually going on. So it looks like a lot of words, but all we're really doing here is calling this train test split method from sklearn. So basically sklearn is the library, and from that we imported this model selection module, and then within that module we have this train test split method. Hence why we're calling model selection dot train test split, since we're accessing that method. Then we feed this method 3 arguments that we actually care about. The first argument, x, is just our x column that we made up here, so our resource column. The second argument, y, is just this column up here, so our total score column. And then just as I mentioned before that we need to split up the training test and the testing sets, we need to specify how big we want each set to be. So the training set will typically be much larger than the testing set, so we're going to set our testing set equal to be 20% of our data set by writing test size equals 0.2, meaning the remaining 80% of our data set will be the training set. The nice thing about using this function is that it randomizes which values get moved into the training versus testing set, so we can run it multiple times if we want to gauge its accuracy over a multitude of runs. So what does this function actually do when you give it all 3 arguments? Well, what it does is it returns to us 4 values. It will give us all the x training values, all the x testing values, all the y training values, and all the y testing values, and it does so specifically in that order. So what we're doing is doing a multivariable assignment here, making 4 new variables that represent these return values, separating them by commas, and then assigning them to the results of this function. So now that we have this line, we've made our training and testing sets, we actually have everything we need to go ahead and make our linear regression now. To do that, all it takes is actually just one line. Let's make a new variable. Let's just call it linear. And we're going to set it equal to linear model, which is the module we imported from sklearn. And then we're going to call a linear regression function like this, just like that. So this line simply grabs a linear regression method from sklearn, so we're making a new model and assigning it to our linear variable. And then to actually train our model, it's just as simple as writing one line. So down here, I just want to type linear.fit, and then all we need to pass in is our x training values, and then also our y training values. We want to pass in the training values when we're fitting it because, as evident by the name, these are the values we're training the model with. Once this chunk of code is run, like this, go ahead and run it, we've now actually fully created our linear regression in just a couple of lines of code, and now we're ready to go and look at what our linear regression actually looks like and what its score is. So how do we go from here? Because it looks like right here, it didn't actually print anything off, so how do we know anything about our model? Let's print off some things from it now that it is trained. We mentioned earlier that the whole point of looking at linear regressions was to find the y-intercept value and the slope that made the line the best possible fit. So now that we've trained our model, we can access those values. So here's how we get the coefficient or the slope, and then also the y-intercept. So I'm going to go down in here, this line. I'm going to write print, let's just say, let's get the coefficient or the slope first. All we need to do is coef, and then with an underscore, and then to get the y-intercept, all we need to do is type print linear.intercept, also with an underscore. And make sure to remember the underscore at the very end, because if you don't have it, it'll give you an error because it won't recognize it. And then just so we can format this actually a little bit nicer, I'm going to add like a string here. I'm just going to say, let's say slope slash coefficient in this one, and then do a little, that should work here like that, do a comma like that. And then I will have another string here that says y-intercept like this, and just do it like that. And then if we were to actually run this code chunk now, you'll see that our slope or coefficient is equal to 0.813895, and then our y-intercept is equal to about 10.54. So what this means basically is that if we actually had our equation, that our linear regression equation would be equal to y equals 0.813895x plus 10.54456, like that. And this would actually be our linear regression equation that we found using this model. So this is cool to know, but how do we actually know how good our model is? Let's check it out. So to find the accuracy of the model, we need to pass in our testing sets of data to the score function. So let's actually go down here. And let's go ahead and just say print. We're going to do score, and then a comma here. And then to access the score, all we need to do is type linear.score, and then we want to pass in our testing value. So I'll say x test and then y test. And then if I run this, oops, remove that call in there. Okay, run this again. Okay, and you see that our score that we've gotten for our model is approximately 0.83. So one issue that we may run into with our data set is that since it's so small, if we're trying to score our data set, using a simple linear regression is going to have some drastically varying results. So if I keep printing this off, it's going to keep printing the exact same number. However, I could actually retrain the model and then run this score again. We could get a whole new score. So to show you that, if I go up here, I can rerun the code here. Let's just reprint off our intercepts and slope because it'll change a bit. Run it again, and this time we got 0.67, which is much lower than the 0.83 number we had. And for this score, the higher number, the better. So a score of 1.0 would be like a perfect score, and then a score of like 0 would be like an awful score. That's like absolute lowest you can get. So the 0.83 was a lot better than 0.67, but I could literally just keep running this over and over, and then getting different scores because it is selecting, when you do this train test split here, like I said, it randomizes it, so it's going to be different each time for the score. But I could literally just keep running this over and over again. That time that's really low, like 47%. Let's just run it and see until we can get like a better score. So this time we get like a 92%. So let's go ahead and just stay at there for a moment. So the score isn't exactly a percentage, but you can kind of think of it like that. Obviously the higher number being better. And then what the score is kind of pretty much saying is that given your model, like for our model specifically, if we took a research variable, we could, with about 93% certainty, predict the total score variable. Generally, you want to shoot for a score of at least 0.5 because that's a score that's at least decent and showing some degree of correlation. Anything above like 0.75 is considered probably a good model, and then everything above like 0.9 is considered great or like a very good model. And remember, all these scores are in reference to the correlation between two variables. So certain independent variables will have lower or higher scores than others. But as seen by our previous correlation episode, the research column is probably going to yield our highest score, hence why we used it in this model. If we were to modify our x variable and make it something like talent instead, the score would change. So let's take a look at our actual scores were versus our predicted scores. So to do that, let's go down here, and we can actually just use sklearn's predict function. So we'll just make a new variable, let's just call it predictions. And we're going to set it equal to linear.predict, and then here we just want to pass in our x testing values. So then let's loop through all the predictions and print off both the prediction and the actual value for each entry. So to do that, what we're going to do is write a loop here. We're going to say for x in range, and we're going to do it in length of prediction. So we run through every single prediction we've made. And then we'll just do obviously an indentation here. And then what we want to say is, let's just print off the predicted values versus the actual value. So I'm going to say predicted value like this, and then comma, we'll say, so predictions x here. We'll do a loop, and then we'll say actual value, and then comma, and then the y test here will be our actual value. So basically all we're doing here is looping through every single prediction, and at each prediction we're printing off what the predicted value was versus what the actual value was. So now let's actually run this code and see what happens. Okay, so you see it prints off a whole list here of each of our x test values and their corresponding values. So if we look at these, we can see that pretty much all of our predicted values are somewhat in the ballpark of the corresponding actual values. So for instance, if we look at the first predicted value, we predicted this would be a value of 30.51 for total score. The actual value was 34.42 for total score. Let's go down a little more. We can see, like right here, we predicted a total score of 13.18, but the actual one was 11.79. And then let's look at this like one more. Let's say this bottom one here. We predicted a total score value of 30.30, and then the actual value was 31.36. So generally you can see that all these values, all the predicted values I should say, are all relatively close to the actual values that we're seeing. And this is actually the sign of a decent or good model. If we were to have a lot of values that were wildly off, because keep in mind like this would be out of a scale of 100 because total score is 0 to 100. So if we had like a predicted value of like 30 and then our actual value was like 80, then that would be really bad because we're like way off on the prediction. But as you can see from all these, we're actually decently or relatively close on almost all of these. So something that would be super helpful would be the ability to just plot these correlation scatter plots with our new linear regression line added to it to help us visualize how effective our model actually is. So let's go down here to our actual new code block, and I want to make a scatter plot that just takes in the training values of x and y. So let's say plt.scatter. We're going to pass in the training values of x and y, so basically the bulk of our data set. And then what we want to do is plot a line that shows our linear regression model. So it'll basically be corresponding to the predictions that we made. So let's do on top of this scatter plot, we'll do another line. We'll say plot. Then we're going to pass in our x testing variables as well as the predictions we have made. And then at the very bottom, like usual, we're just going to type plt.show like this. And then now if we actually run this, you'll see that we get our original research and total score correlation graph, except this time it now has our linear regression line added to it. Let's go ahead and just add some labels real quick. I'm going to add plt.xlabel. I'll just call that research. And then these will obviously be just to help us look at the graph a little neater. Say total score. And then I'll write plt.title. And we'll do total score versus research with linear regression like this. And then when we run it, same exact thing, except now we just have labels on our graph. So what is this graph actually telling us? Well, each of these individual little points, or the dots you see from our scatter plot, are coming from our training set and represents the vast majority of our data points and where they fall. And then this line represents the linear regression model using our x testing values and our predictions to try and fit a linear line, or sorry, a linear function to all the data points, which is in the form of a line. One thing you may notice is that because the predictions don't go on for infinity, the line simply stops at its last point. If we, however, wanted to continue this line to infinity and then all the way down to its intercept point, we could just add one line of code to this. So there's a function in the material plotting library that is called axLine that helps us continue a line infinitely. All we need to do is give it the slope and the intercept, and lucky for us, we've already found those things. So to do that, let's call our plt.axline function and just pass in our intercept and our slope. I'm going to type plt.axline, and then what it wants for the slope is an argument called xy1. So I'll say xy1 equals, and then we want to pass in a coordinate which represents our y-intercept. So our y-intercept is always going to be where x equals 0, and then whatever our actual intercept value is. But we want to make sure we convert it to a float. So let's do float linear dot intercept like this. So this would be the coordinate of our y-intercept. And then what we want to do is then pass in the slope of the graph. So we're going to say slope equals, and then we're going to pass this in as a float as well. And then we're going to say linear dot cof to get our coefficient or our slope. So again, all we're doing here is passing in two arguments. We're passing in the intercept and the slope. The intercept is just this xy1 argument here, and we're just setting it equal to a set of points that has 0 for the x-coordinate and our intercept for the y-coordinate, as all y-intercepts always have an x value of 0. Then we just pass in the slope as our second argument here, which is just the coefficient of our model. We wrap both of these numbers in a float method because we're converting them to floats, otherwise it'll give us a warning. So now if we actually run this graph, you'll see that we now have a regression line that goes all the way from our y-intercept all the way up to infinity. And that's pretty much it for simple linear regressions. We learned how to convert the Pandas data frames into Numpy arrays, use those to generate our training and testing sets, and then use those to fit our model and then look at all sorts of scores and this visual aid to help us see the accuracy of our model. So one last thing I actually want to do is look at the idea of multiple linear regressions. And it's actually almost the exact same steps, except in multi-linear regressions, we just select multiple x variables instead of just one. Because it follows pretty much all the exact same steps, I'm just going to modify the code we've already typed instead of typing up a bunch of new code. I'm going to go ahead and just go back up here to this chunk where we're actually making our model. So to do that, let's go back up to our x variable here, and let's actually select multiple columns instead of just one. So I'm going to remove this reshape thing. Instead of having to do like a single selection, let's do a multiple selection thing. Let's use a lock function to get let's get every single row, and then all the columns or all the variables from, we'll say talent all the way to commercial. And then we're doing this so we can look at every single numerical column besides total score and see how all these factors in combination are able to predict the total score. Because if we go up here to our data set, scrolling, you'll see that, yes, all the numerical columns, it's everything from talent to commercial, and we want to use that to predict our total score. Hence why down here, we are selecting every column from talent all the way to commercial. And we don't need to worry about actually using this reshape function if we're selecting multiple things, because it's already more than one dimension. And so from that point on, everything else is the exact same, and we actually already have our multiple linear regression model. So let's run this chunk of code to actually fit our model, and then let's print out the coefficient and the intercepts. And now it looks like our coefficients are these numbers here, and our y-intercept is this number here. So what this actually does is whenever we have multiple variables, we're actually going to get a coefficient for each variable. So we should have 7 variables total, I believe, because we have 7 columns. So for instance, the coefficient for like talent, for instance, would be this number. And I believe our second column is, second column should be infrastructure. So it would just go in order. So this is our infrastructure number, and then like our research number, I believe, or operating environment, whatever the order is of the column. So basically, yeah, each variable has its own corresponding coefficient, and then we have one y-intercept as usual. So next, let's take a look at how good our score actually was. Let's print it off here, and wow, okay, so it looks like our score is 99.99999%, which is a very high score. And what this means is that given the value for all of these numerical fields, we were able to guess what the total score will be within 99% accuracy, pretty much. So this actually should be pretty self-explanatory, and it's actually a little bit like redundant doing this model selecting all of the numbers, or all the numerical columns, because if we think about how the data set works, the total score is literally just based off of the numerical score of all the other fields. So this number, so when we look at like our data set, and let's take for instance the US, we look at all these numbers basically culminate to like make our total score. So it makes sense that if we're taking in every single one of these variables, we should be able to predict our total score almost 100% correctly. And our model actually does reflect that pretty well, because obviously we have an accuracy of almost 100%. But in general, multiple linear regressions are going to be more accurate than single linear regressions or simple linear regressions. And this can obviously kind of vary case by case, but generally it holds true, because if we're factoring more than just one variable, it'll typically only make the model get more accurate, because we're just basically feeding it in more data. So if we go ahead and just run our loop again, you can see the predicted values are actually very, very close to our actual values. And when I say very close, I mean pretty much exactly. Like, right, let's look at, for instance, like this one right here, predicted 15.487, actual value is 15.48. Right here predicted 31.3599 is 31.36. And honestly, I think this model probably does have 100% accuracy. The thing is, the reason why it's not perfectly 100 is because of the rounding. I'm guessing these scores here might be rounded for what we have in our actual columns, which is why our predicted values go a bit further in decimal place, but are actually pretty much exact if we were to round on most of these. This is technically the very last episode in the series, but we're actually learning new things. As the next episode, the definitive last one, will just be us going over everything we've learned with a brand new data set and piecing it all together. Before we wrap up with this dataset though, let's write up a super quick and simple analysis of the dataset we've been working on throughout this series. So as a fun little experiment, I actually plugged in basically the dataset that we had and some of the information from it into ChatGPT, and here's what I got as a basically a dataset summary. So it says the analysis of the dataset tracking the AI global index of 62 countries revealed interesting insights into the factors contributing to a country's total score. Among the various fields evaluated, such as talent, research, and operating environment, it was observed that a country's total score displayed a strong correlation with both talent and research. A simple linear regression model achieved an accuracy of approximately 75% when using research as a predictor for the total score. However, the accuracy significantly improved to 99% when employing a multiple linear regression model that incorporated all the scored fields to predict the total score. These findings highlight the crucial role of research in determining a country's overall AI capabilities, while also emphasizing the combined influence of multiple factors in shaping its performance. And with that, we'll formally wrap up this episode. In this episode, you learned about simple and multiple linear regressions, how to train them, how to test them, and how to view the accuracy of the models in both number form and graph form. I strongly commend you if you made it this far in the course, as I know it's not easy to learn something new, especially something that can be pretty intimidating like data analytics. In the very next episode, we'll summarize everything we've gone through by walking through a brand new data set, employing everything that we've learned so far. I'll see you in the next one. Hey everyone, and welcome back to the final episode in our Python data analysis series. In this episode, we're going to try and piece together everything we've learned to find a new data set and do some data analysis on it. Since we've already performed all sorts of basic analysis on our AI Global Index dataset, let's find a new one on Kaggle so that we can all go through a new dataset together for the very first time. After doing a little bit of searching, I found a dataset that I think would be interesting for us to use. Instead of an AI Global Index for the world, it's a World Happiness Index. It ranks each country in terms of how happy the average citizen is and has variables like economy, health, family, freedom, and more. That might give us some insights into how these general factors for a country might impact how happy its citizens are. I'll put the link to this dataset in the description below if you'd like to work alongside me in this video. Once you have the dataset downloaded, let's hop right into our code so we can start exploring. So the first thing we want to do is import all the libraries we're going to be using so we don't have to worry about adding them later on. If for some reason we miss some of them, we can always add more to this first code block. So we know we're going to need to upload our file. So just like the other episodes, let's add a Google Colab import here. So we'll say from google.colab import files. And then we also need to import IO to read the file. So I'll just say import IO. And then we'll need to get our most valuable library, which is pandas. So I'll say import pandas as PD. Next, we're going to be doing some plotting using material plotting library and Seaborn. So let's add those two imports. So for material plotting library, we'll do the same as before, and we'll say import matplotlib dot pyplot. And then we'll also do import Seaborn. Spelled that wrong. Import Seaborn as SNS. And then after that, we're going to be using Numpy for our regression arrays. So I'll also add a Numpy import. I'll say import Numpy as MP. And then for the very last import, we need to import some models from Sklearn to actually do our predictive modeling. So I'm going to import individual modules from this. So I'm just going to write from Sklearn import, and then we'll do the same ones as the last episode, model selection, and also linear model. So model selection is the module used to split up the training and testing sets, and then linear model is the module to actually build a linear regression, just for a quick review from last episode. So I know this might be kind of a bit confusing or overwhelming at first to have all these libraries kind of here bunched up at the very top, but now that we've got them all ran in one block, it'll be nice so we don't have to worry about it later on in our code having to add libraries as we go. So under all these imports, we'll make a variable. Let's just call it data file, just like we did the first time. And then we're going to set it to equal to files.upload. And then this will obviously call our upload function from Google Colab to upload our CSV file. And then right underneath this, let's make another variable. Let's call it df. And then I'm going to copy and paste this line here. So this line is the exact same line we used to actually read the file for our AI global index, except the only difference is that it has its title changed. So now it's just World Happiness 2016.csv, which should be the name of the file once you download it from Kaggle. Okay, so I went ahead and just ran this code block and then selected the World Happiness 2016 CSV file. So now we should be good to go. So the first thing I usually do with a new data set is just see what it actually looks like. So let's just call a function here. Let's say df head, and let's just pass in 10 for this so we can see the first 10 entries in the data set. And voila, here's a data set. So this is what it actually looks like. We have many countries of the world, and they're by default ordered by their happiness rank, with Denmark being 1, Switzerland being 2, Iceland being 3, and so on. And right away, before even looking at the other variables, we can see that all the top 5 happiest countries in the world come from Western Europe, which may be an interesting thing to explore in just a little bit. If you look beyond just the rankings, you can see the actual happiness score that each country is ranked with. So obviously a higher score correlates to a lower numerical rank. Then you have lower and upper confidence intervals here, which for a more complex analysis may be helpful, but since we're doing a kind of a more basic analysis for beginners, we're probably not going to be using these columns a whole lot. After that, we just have a couple of variables to look at that could be correlating variables to happiness. So we have economy, we have family, health, freedom, trust, generosity, and dystopia residual. These all appear to be based on a scoring system, but it's not immediately obvious to me what scale they're based on. Some look like they're based on a scale of 0 to 10, and others look like 0 to 1, and some look just somewhere in between. So purely out of curiosity, I'm going to go ahead and just make a new code block here, and I just want to see the bottom 10 entries. So I'm going to do df.tail, and I'll just pass in 10 like this, and then we'll take a look. So if I run this here, these should be the 10 unhappiest countries in the world generally, with the bottom few being Togo, Syria, and Burundi. So these countries all fall in Africa, which may be another interesting region to explore in a little bit. So now let's try and get a better idea of what our data set actually is. So you've seen it now, but let's look at some descriptive numbers to get us a better understanding. So I'll make another code block down here, and we're just going to call our df.describe function that we've done so many times before, just to give us a quick summary of the data set. So if we run it, we'll see that we get a nice summarized table of all its attributes. So it looks like there's 157 total countries in the data set because each column has 157 entries within the count variable here. Let's keep in mind that there are, I think, approximately 195 countries in the world at the moment. So there are a fair chunk of countries that aren't actually on the data set and don't have data collected for them. So we are missing a decent amount of countries. So can you just keep that in mind? Let's look at some mean values here for a minute. So it looks like if we look at the mean overall happiness score for the entire world, it's about 5.38, which should, somewhat make sense if the scale is from 0 to 10. So let's look at actually the min and max of happiness. So it looks like the min, so the min here is 2.90 for happiness score, and then the max is 7.52. So it's probably likely that the scale is out of 10. Then of course we have the percentiles in each field. So we can look at like 25, 50, 75%, things like that. So just for example, with our percentiles, it looks like to be like in the 75th percentile of happiness, you have to have a score of at least 6.269 or above. And then to be, if you want to be in the bottom 25%, you got to have 4.405 or below, and so forth. If we look at the min, especially in the fields like economy, family, health, and freedom, it looks like a lot of these, actually, pretty much all of these, have a minimum score of 0, which shows that there are some countries that, for certain measurements, are at the absolute lowest possible value they could be at. So next, I know we can see all of our column titles already, but let's quickly print off a list of our column titles because I want to see them as strings because it looks like some of them are kind of long here, especially the ones that have like parentheses here like this. I just want to take a look at what the actual like string values are. So I'm going to type df.columns just to get the column titles and then run it. And then, yeah, so it prints out an index list of all the names. So we have country, region, yada, yada. So just looking at this, I can already see it definitely might be a big inconvenience for like fields like economy, where there is parentheses here, having to like type everything out with parenthesized text. Because if I want to access the economy column, I don't want to have to type economy and then parentheses GDP per capita. It'd be nice to just type, just economy by itself. And then same goes for like health here, also has parentheses in it. And so does like trust and those other columns. So to fix this, let's actually change some of these column titles. So I'm gonna make a new code block down here where we can call the rename function. And actually first, I'm gonna make a copy of our data set just so we don't corrupt the original data. So let's make a new variable. I'm just gonna call it dataset. And again, this is not like the greatest naming scheme. I'm just kind of doing it for the sake of this video. I'll say dataset equals df.copy like that. And then I'm just gonna run this just so we have it now. And now we have our copied dataset. So I'll make another code block after this actually. And then I'm just going to write dataset.rename. And then inside, we're going to want to specify what we're renaming, and that's going to be columns. And then what do we need to do here? If we look at the Pandas documentation for the rename function, it wants a dictionary of key value pairs for each column, where the key is the old title and the value is a new title. So it should look something like this. So we'll have squiggly brackets to signify a dictionary. And then for the first key value pair, let's do health. We'll say health, parentheses, life expectancy. I believe there's a space here. It looks like there's a space. Yeah, okay, there's a space there. Okay. So do health, life expectancy, and then we just want to change that just to say health. And then let's do, next we'll do economy, which is space GDP per capita. I believe it's, okay, yeah, making sure. So the P is not capitalized, but the C is. So we'll do this, and then, oh, I messed up there. GDP per capita, and then we'll say rename it just to economy, so we don't have the extraneous stuff. And then lastly, I want to do the trust column, so I'll say trust, and that's government corruption, like this. And then I want to have that replaced with just trust, like this. And then I want to modify this data set directly, so I'm going to add another argument here. I'm just going to say the in place argument. I'm going to say in place equals true after I pass in the columns argument. So then if we actually run this block, we should now have a data set with the columns renamed to be simple titles instead of having parenthesized text. So just to show you what the new thing should look like, let's just print out head of dataset. So I'll do datasets.head like this. And now if you look at it, we've now replaced our columns with some simpler names that aren't as hard to type. So economy, which was economy GDP per capita, is now just economy. And then health is, just health now, then trust is just trust, and so forth. So it's a little bit simpler and a little bit nicer to read. So one more thing I want to do with this data set in terms of kind of just getting it cleaned up is I want to drop some of the columns. So I mentioned that we're probably not going to be using these lower confidence and upper confidence interval columns. So let's just go ahead and get rid of these columns to make the set easier to look at. So actually in this same code block, I'm going to go actually make a line here. I'm just going to call dataset.drop. I'm going to say dataset.drop. I'm going to pass in a columns argument. And then we're just going to want to pass in a list of the columns I want to drop, which is just going to be 2 of them. So I'll say lower confidence interval, comma, upper confidence interval. And then, again, we want this to be modified directly. So I'm going to say in place equals true like this. So I went ahead and ran this chunk, and you can see now that it looks quite a bit nicer since we have, obviously, our column titles replaced, and now we drop the 2 extraneous columns that we're not really going to be looking at throughout this episode. Now that we've done a little bit of data cleaning, I want to take a look at some statistical analysis information. So I want to look at like the mean, median, and standard deviation of some of these columns. So we already did a little bit of this earlier with our describe function that we have here, but I want to actually just look a little closer at this. So I'm going to make actually, let's say 3 new code blocks for each function. So I'm going to have like one of these blocks. I'll have this as the mean block, median, and standard deviation block. So in these functions, we want to select only the numerical columns, or else, like last time, we'll get a warning that we're trying to calculate the mean on things that aren't actually numbers. So in this first code block, let's just write, let's say datasets.lock. Then we're going to select everything from, we're going to select every single row and then every single column from happiness score all the way till the end like this. And then we're just going to call the .mean function on it like this. So we could specify dystopia residual here in this thing like this. Like we could type dystopia residual, but it's actually not necessary if we do nothing after the colon because it'll just autofill to the very end. So we don't actually need it because it'll go to the end of list like this. And then before I run this, let's actually copy this line here. I'm going to paste it into these two blocks here, and I'll just change these. So this will be median, and then this one will be STD for standard deviation. And then I'm going to run all these blocks. So I'm going to run the mean block here, run the median block, and then run the standard deviation block. So for instance, looking at the mean, it looks like the average happiness score is 5.38. The average freedom score, for instance, is 0.37, and so forth. So it definitely helps to see all the means side by side like this, as it helps to give us kind of an idea of what the range of the numbers kind of looks like in each of the columns. And then, as expected for looking at median, the median numbers are actually fairly close to the mean numbers. As we know, the median is just the middle number in a list in sorted order. And then lastly, of course, we have our standard deviation scores for each of our variables. Which, if we're looking at this right away, it's obvious that happiness score is the most variated out of all the variables. So next, I want to do a little bit of selection and sorting to get an idea of what the highest and lowest of some individual fields might be. I want to make a new code block actually right here, where we can go ahead and do this. So let's first select the country and happiness score columns and sort them in order of highest to lowest happiness scores. To do this is pretty simple. But first, I'm going to select these two columns. I'm just going to write, let's say, dataset, and then pass in a list here. I'm going to say country, and then comma, happiness score like this. And then we want to call this function sort values. And then we're going to sort it by, let's say, happiness score. And then we're going to do ascending equals false. And I'll explain what all these mean in just a second, so bear with me here. And then I'm going to say dot head like this. And then if we run it, you'll see we have Denmark, Switzerland, Iceland, Norway, and Finland here at the top. And then we have Benin, Afghanistan, Togo, Syria, and Burundi here at the bottom. So basically what this line is doing here, let's break it down step by step. So all I'm doing here is selecting both the country and happiness score columns, and then I'm calling this function that is called sort by, and then it'll basically sort a list of entries in order based on a certain variable. So I'm just saying sort by the happiness score, and then we're going to pass in ascending equals false. If I did ascending equals true, it would actually do the opposite of this, so it would show these ones at the bottom here first, because this is actually technically ascending. If we're starting here, this is the lowest number and this is the highest value, so it's ascending. We want it to be descending, so hence why ascending is equal to false. And then we're just doing dot head, which obviously will print out the first 5 entries. And I actually didn't realize I made a little quick fix there of putting the parentheses here. I guess if you don't put the parentheses there, it prints it off like this in kind of an ugly way. But if you do a parentheses, it makes it a little better, just like this in our regular table format. So I want to look at actually now the bottom 5 countries like we just did. However, I want to do it in this kind of similar format. I'm going to make a new code block here. I'm just going to copy and paste this. And instead of dot head, I'm just going to fill this with dot tail like this. So if I print this off, as we saw before, the lowest countries in here are Benin, Afghanistan, Togo, Syria, and Burundi, with the lowest score being 2.905, which is the lowest score in the whole list. So we already knew this from our original tail call, so let's actually look at more variables besides just happiness score. So to look at some other variables, let's make a new code block here. We're going to do kind of a similar thing. I'm just going to copy and paste this right into here. And then let's say instead of looking at like happiness score, let's look at economy instead. But we still want to see like the country, so I'll keep the country column in there. And then let's say we want to sort by economy as well. And then we want to look at the first 5. So I'll make sure it's head and not tail. And then if we actually run this now and scroll down, it looks like Qatar, Luxembourg, Singapore, Kuwait, and Norway all have the best economy scores. So the numbering here on the left indicates its actual index, which again is based off of its happiness rank. So what's interesting is that places like Qatar and let's say like Kuwait, for instance, are top 5 in the economy scores, but are kind of almost like middle of the rung or kind of a little bit towards the top in the overall happiness index. And of course, we could change this function to tail instead of head to see the worst 5 economy scores on the list. So we'll do dot tail, and it looks like we have like Liberia, Malawi, Burundi, Congo, and then Somalia as the bottom 5. And then let's just look at another variable real quick. Let's look at health instead of economy. So let's put health here, and then we'll say obviously sorted by health as well. Let's look at the top 5. We're doing dot head, and then let's go ahead and run it. And if we run it, it looks like, let me double check. Yeah, so it looks like all these top countries, except for Spain, are all from Asia that all have the highest health score. So that's kind of an interesting thing that we can kind of keep in mind maybe for the future. And then let's look at the bottom 5 actually. Let's say dot tail. Let's look at these bottom 5 ones. And it looks like pretty much all of these countries are from Africa. So we got Nigeria, Angola, Ivory Coast, Chad, and then Sierra Leone. So that's kind of an interesting thing to look at. There certainly seems to be some sort of correlation here with the region they're in. As we look at, again, like head, these are pretty much all Asian countries besides Spain. And then so these have the highest health scores. Then we look at the lowest health scores, and they all appear to be in Africa. So one thing I actually want to look at real quick is kind of just compare the regions of these scores. It definitely seems like some regions tend to fare better than others in terms of certain variables. So it makes me curious to see what it would look like if we just compared regions completely. So to do that, I'm going to just make a new code block down here. And I'm going to call the group by function that we looked at in one of our episodes. So I'm going to say datasets.group by like this. And then we're going to group these together by region. But doing this just by itself won't actually really do anything because we need to do some operation with the data. So I'm going to add dot describe like this. And then if we go ahead and print it off, it'll give us a nice describe table like we saw before, except now it grabs all the countries in a particular region and then groups them together. So we have like for one region, Australia and New Zealand, Central and Eastern Europe, Eastern Asia, and so forth. The only issue is that it does this describe function for every single column. And as you can see, these 3 dots here basically show that there's an overflow. So we're missing a lot of this table just because we can't actually see all of it. So just to narrow this down, let's actually just select the happiness score so we don't have all the other variables taking up space. Of course, we'll need to select a region as well if that's what we're grouping by. So to do this, I'm just going to add a double bracket here. And let's get region as well as happiness score. And then now if we run it, it only prints off the happiness score summary for each region. And this is pretty helpful to see actually. However, in our case, let's say we only care about the mean value from this table. So let's actually do something else here. I'll make a new code block, and I'm going to copy and paste this line. But instead of doing describe, I'm just going to type .mean like this. And then if I go ahead and run it, now we have the mean of each region. However, it's not sorted in order, so let's do that super quick. So to sort these actually in order, let's just add another function here. Let's just say sort underscore values, and then we're going to sort it by the happiness score ranking, because that's what our table actually includes. And then we're going to say, same as last time, we're going to do ascending equals false. So we have the highest entry at the very top. So this looks like a super long line of code because we're literally calling like a bunch of different functions on it. So we're first basically just selecting the columns we want, and then we are grouping them by the region. We're getting the mean of each group, and then we're sorting that mean where we have ascending false. So the highest entry will be at the top, and the lowest entry will be at the very bottom. So just so you can see, let's actually run it now. And now it looks like we have a sorted table of which regions have the highest to lowest happiness rating. As you can see, Australia and New Zealand are at the highest, followed by North America, then Western Europe, and so forth, with South Asia and Sub-Saharan Africa being at the bottom. So again, all these numbers are actually showing us is the mean happiness score of each region. Let's say, for instance, we want to keep the same exact sorting scheme, but we want to see the entire data set instead of just these 2 columns. To do that, we could make a similar code block here, where we could literally just copy and paste this here. But instead of just selecting region happiness score, we can just select the entire data set. So I can just select the entire data set like this, and then I could print it out. And now you can see the mean stats of every single region, but still sorted by happiness score. So obviously we've got happiness score here. That's what determines the ordering, because it goes 7.32, 7.25, 6.68, and so forth. And then we also have the other mean variables, so like economy, family, health, freedom, and so forth. So just to give us a little bit of help with this, let's actually plot this graph just so we can kind of visualize each region. So I'll make another code block down here, and I'll make a new variable too. I'm just going to set it equal to what we were doing kind of up here with the means and the regions. I'll make a new variable. I'm going to call it mean regions equals datasets. And I'm going to group by regions again. I'll say by equals region. And all we're going to do is just call the dot mean like this, which if we write that off and then we, let's say, print regions, and we print it off like this. Actually, I can probably just do it like this. Set out a print statement. If we do it like this, you'll see it's the same exact table as the one right here. Although, of course, it's not sorted in any particular order. So next, let's actually use PLT or material plotting library to plot this. So I actually want to do a bar graph. So I'm going to go ahead and just delete this. I'm not sure what I'm going to do in a second with the bar graph. So I'm going to type plt.bar. And then remember, with a bar graph, we want to type in the labels as the first argument and then the actual data numbers as the second argument. So for the first one, we need to get the region labels. Unfortunately, we can't just pass in the region column because when you use group by, it doesn't actually classify the grouping variable as its own column, but rather it indexes it by that. So for our labels, we actually need to pass in mean regions like this, and then we need to call .index to get the row labels because technically they are indexed by those titles. So instead of just selecting the region, we just type .index instead, and that'll give us the labels that we need. And then for actual data numbers, we actually can just select the happiness score column. I'm going to do mean regions like this, and then we're selecting happiness score like this because we're basically selecting this whole column here. If you can see like where my mouse is, we're selecting this happiness score column, so we're passing that in as our second argument. And of course, like always, let's add some labels to help us out. So I'm going to write plt.xlabel, let's call it region, and then plt.ylabel, and then let's call it mean happiness score. And then we'll do lastly plt.title and we'll say mean happiness score of each region. And real quick, looks like we're getting a little thing here. PLT is not defined. Let me go back to the top here. Import Matplotlib. Oh, oops. Should have added that as PLT here. So let me actually rerun this because it didn't quite import our material plotting library correctly. Let me reselect this. And then I'll need to rerun the line where we're actually modifying dataset. Dataset.copy, and then let's rename and drop. Okay, so now we should be good. The PLT should be good to go now. So let's go ahead and actually just type plt.show here at the bottom. And then let's go ahead and actually just run it and see what it looks like. And voila, here we have our graph. Obviously, there's one big problem, however, and that's that these region titles are severely overlapping one another, and they make the graph pretty much impossible to look at, and it looks pretty awful and pretty ugly. So there are ways to work around this using some functions, but we're going to take the easy way out and just turn this into a horizontal bar graph instead of a vertical one. So I'm just going to add a bar h right here instead, like this instead of bar. And then I'm going to swap these y labels and these x labels to be a bit more accurate. So I have this like this. And then now if we run it, we can see our graph looks a whole lot better. As you can see, Australia and New Zealand is neck to neck with North America, beating it only by a tiny margin. Then we've got, for instance, Western Europe in third, and then so on. And it looks like, just like we were looking at before with our data and tabular format, it looks like the African regions tend to be towards the very bottom in terms of mean happiness score. Now that we've explored some of the stuff in regards to each individual region, let's actually start looking at some correlation between variables and some predictive analysis. Just like we did with last time, let's use the pair plot function from Seaborn to check out the correlation between two different variables. So below all these graphs here, or I guess I should say the single graph here, I'll make a new code block, and then let's start looking at the Seaborn graph. So I already imported Seaborn as SNS, so I'm going to call SNS and say SNS dots, and then pass in, let's do pair plot, and then pass in our data set that we have here. And then if I run this code here, just like last time, it'll take a minute since there's a lot of computation, but it'll spit out a correlation grid in just a moment. Okay, so I went ahead and fast forwarded a bit, so now we have our pair plot here, and now it looks like we have a ginormous grid, so let's actually sit down for a second and analyze this. So one thing I can note like right away in this pair plot is that if you look at these first two columns, which should be, first one's happiness rank, and the second one is happiness score, that these are practically mirrors of each other. So if you look at like the economy line here, it looks like happiness rank and happiness score are exact mirrors, and then same with family for happiness rank and happiness score. Hopefully this makes sense why it's like that, and that's because the happiness score directly impacts the happiness rank of a country, so the reason they are mirrored is because they're pretty much inverses. So in a ranking system, 1 is considered the highest, and the higher the number, the worse rank you are, technically, numerically, whereas in the score field, a higher number is better. This means that a high happiness score correlates to a numerically low happiness rank. So for example, I believe it was Denmark that had the highest overall score, means they technically have the lowest overall rank numerically, even though it's rank 1, which stands for the best. So, in terms of actually looking at our correlation analysis and trying to find some graphs that might work, I think the variable I really want to look at here is happiness score. We could use happiness rank too, but score offers, I think, like a more kind of just definitive and specific number that we can measure. So, because of this, we want to find graphs in this pair plot where the happiness score is on the y axis so that it is the dependent variable, which means I kind of want to look at ones here in the second row, which has happiness score as the dependent variable. So, let's actually scroll down and see which columns are which. So we got economy, family, health, freedom in that order. Then if we go back up to our happiness score here, it seems to me that economy and health are the two most correlated with happiness score. So what I mean by that is this: if you look at the second row here, the third column from the left and also the fifth column from the left appear to be the most correlated. It looks like family is definitely correlated as well, but maybe not as strong, maybe not as heavily as economy and health are. So let's just go ahead and keep these three graphs in mind here when we dive further into some correlation exploration. And so by those three graphs, I just mean in this second row here, the third, fourth, and fifth columns here. One thing I'm realizing as I'm looking at this is that it seems like things like economy, family, and health are all generally positively trending together. So if you look at the rows between economy and health, which should be like economy on this y-axis here, and then health on this axis, so it's the fifth column over in this third row here. This tends to be, or this actually looks like quite a positive and like tight correlation. So even though this data set is meant to explore happiness rankings of countries, we could also use it to explore some of the other factors that impact each other, like these variables like economy and health, for instance. So, for example, maybe we could ask, how does a country's economy affect the health of its citizens? In fact, if we look at the intersection of health on the y-axis, where we have health here, and then economy on the x-axis, which should be this third one here, looks like there's actually a very tight correlation between the two, suggesting a good economy may lead to stronger health numbers. So now let's do the same thing we did with our last data set and use this pair plot function to help us plot out some individual charts. So there's actually three correlations I want to look at in more detail here. So I want to look at the correlation between economy and happiness. So let's go up here. So economy and happiness is one. I want to look at the correlation between health and happiness and also the correlation between economy and health. So I'm going to go actually below this. I'm going to make three new code blocks for each one of these graphs that I want to explore, just like this. So in this first code block, I want to make a scatter plot between economy and happiness score. I'm going to write plt.scatter. I'm going to pass in both of our columns here. So for our x column, we want to have economy because that's our independent variable. And then for our y value or our independent variable, or sorry, I said that backwards, sorry. This economy is our x variable, so our independent variable. And then we want to have our dependent variable as happiness score. That should be like this. And then if we actually, extra rows there. And then if we run it, we can see we just reproduce one of the graphs on the grid with economy on our x-axis and happiness score on our y-axis. And just like every other time, let's make some labels. Let's say plt.x label, label economy, plt.y label. Let's just label this one happiness score. And then let's of course type plt.show. And then let's just run it like this just to get a little bit nicer formatted. And now let's look at our other two correlations. So I'm going to copy and paste actually this line here into our other two blocks, and then we can just change the variables around. So in this one right here, let's see, I want to look at the correlation between health and happiness score first. So I'm going to do health right here. And then in this block, I want to change it to economy and health. So I'm going to say economy and health like this. So basically, we're looking at how health affects overall happiness and how the overall economy affects overall health. So let's go ahead and just run both of these and get both the scatter plots for each of these. So we get a scatter plot here between the health and happiness score, and then also a scatter plot here between economy and health. And actually, real quick, I'll just take this stuff up here, just copy and paste it, and I'll change the labels to match. So I'll do paste that in, paste that in. For this one, this is the one that's looking between health and happiness score. So I'm going to say health here for the x-axis. And then for this one, actually I'll run that real quick. Showing us some nice labels. And then this one, it's economy and health. So I'm going to change this one to health just to match the columns that we're actually picking. So now we have labels on this one as well. So as you can see, if you look at all three of these graphs, it looks like all these graphs have a somewhat decent degree of positive correlation, meaning they move up diagonally together. So let's actually see what the correlation is by performing a linear regression on all these variables. We'll do each one individually and see what we can come up with. So first, I actually want to focus on this very first correlation here, and that'll be economy as the independent variable and happiness score as the dependent variable. So I'm going to go down here. Let's actually make a block kind of down here for our linear regressions. So to set our x and y variables, remember we need a numpy array when making these. So for our x variable, I'm going to make it a numpy array. And then all I want to do here is pass in our economy column. So I'm going to say dataset economy. And then remember, we need to reshape it so it is like a column, not just a row. So we'll say reshape -1 to 1 like this. And then we'll do the exact same thing for y. Because I'm lazy, I'll copy and paste it. We'll say y equals numpy array. Instead of economy, we want it to be happiness score like this. And then we're still reshaping it 1 to 1 like this. And then next, we need to get our training and testing splits. So I'm going to copy and paste the same line from the last episode just so we can get this out because I am kind of lazy. So I don't need to type out the entire line. So I'm going to print this out. This is the line, again, like I said, that will split up our training and testing sets and then split up the x and y variables based on what we pass in. And then we can set in the testing side, which is 20%, which means the training size should be 80%. Next, we want to actually make our linear regression model. So we'll do that same as last time. We'll say linear equals, and then we'll call our linear model module that we imported in Sklearn. Let's call .linear regression, as this will actually make our linear regression object. So all we're doing is calling Sklearn's linear model library, and then accessing this linear regression object. And then lastly, we want to actually train the model, which to do that, just like last time, we'll type linear.fit. And then all we need to do is pass in our training values for both x and y. So let's say xtrain and then ytrain. And then if we actually run this code chunk now, we now have a working linear regression model for economy and happiness score. So let's go ahead and see what our coefficients and our slope is. I'll make a new code block down here, and I'm just going to print it off. So I'm going to print, say, linear.coefficient like this. And then I also want to print off our intercept. So I'm going to print linear.intercept like this. And then just like last time, I'll kind of format it a little bit nicer, actually. We'll do, so let's say, slope / coefficient like this. And then we'll have a comma there to separate it out. And then on this one, we'll just say y intercept, and then a comma like that. And then if we actually run this now, you'll see that it gives us the slope of our line and our y-intercept. So again, if we translate this to our y equals mx plus b format, like we have a line equation that's like this, we have y equals mx plus b. What this means with this slope and coefficient is that our equation for our linear regression model we just made would be equal to y equals 2.2 approximately, because I'm rounding, x plus 3.25. Because 2.2 is our slope, which is our b value, and then 3.25, it's our slope, which is our m value, and then 3.25 is our b value, so our y-intercept. So next, just like last time, let's take a look at what our score actually is, so we can see how good our model actually is at predicting these. So I'll make a new block, and I'm just going to type linear.score, and then to score it, we just need to pass in our testing variable to see how good they actually did. So we'll do xtest, and then ytest. And then if we run this here, you can see that we got a score of approximately 0.706. So this is actually a fairly decent score, showing that basically if we were given the economy, we could predict the happiness score somewhat confidently about 70% of the time. So just like how we did before, we look at the different training and testing sizes. And of course, because this function randomizes it, the score can vary each time. So let's actually remake and retrain our model up here. And let's run this score again. This time you can see it's decent, quite a bit worse actually. It's 0.587. Let's just do it again. And I'll just do it a few times. Actually, it's getting kind of worse. I'll do it a few times just so you can see kind of what the score varies to. That's 0.59, 0.57. It looks like it's actually kind of staying around that area now. If we wanted to see a bunch of times running this, we could see kind of the average score over time. Looks like we might have gotten lucky with our first score having it kind of decent. Let's just run a few more. Let's just say like one more after this. And that one is a pretty low score, gave us 0.38, but we'll have to do with it for now. So the reason why it varies so much is because this is such a small data set, and it only has like 150 entries in it. Whereas a lot of data sets you're going to find might have like millions or just thousands. So theoretically, there should be a lot less variance if you have like a ton of entries. But because we don't have that many, there's not really a whole lot of testing and training we can actually do on this model. So it is kind of bottlenecked by that just a little bit. And I actually don't want to get a score this low. So I'm going to run it like couple more times, see if I can get something a little bit higher. Um, let's settle. Okay, that's decent so far. We'll stay with this 0.63 score. So let's roll with this score in this model, and let's use it to actually make predictions for what our happiness scores should be, so we can compare them to what our actual values are to see how accurate our model is. So I'll make a new code block here to actually make our predictions, and so we can print them out. I'm just going to say, I'll just name predictions. I'll say predictions equals linear dot predict. We're just calling the predict function off the linear regression object. And we're going to pass in our x testing values. And based on the x values, it will predict the y values. So just like we did with the last time, we'll make a loop that prints off all of our actual values versus our expected values. If you had a huge data set, you wouldn't want to actually run through a loop and print out everything because there'd be a lot of entries and it'd be kind of tedious to do. But since we have a pretty small testing set, it's fairly small and it actually shouldn't be a problem. So to make a loop, all we'll do is say for x in range, and we'll do length predictions, because we're just looping through every single prediction we've made. And then what do we actually want to do inside the loop? We just want to print off our actual value versus our predicted value. So I'm going to print off the actual value first. I'm going to say actual value, and then comma, and then we want to get the y-test value, because that's our actual value we have for our testing set. And then we will say our predicted value, and then that will be our actual prediction value, like this. And so if we were to actually run this code, it now gives us a list of all the values we actually got versus the values we predicted we would get. And of course, our model certainly isn't perfect. However, it does appear that these predicted values are somewhat in the ballpark of the actual values, showing at least some decent degree of correlation. So for example, we can look at, for instance, like this value here. Let's say we have an actual value of 7.119, but the prediction that our model made was that it would be 6.462. So they're not perfect, but they aren't too wildly off. And of course, it should be noted that all these values that are being predicted and looking at actual are happiness score, because we selected happiness score as our dependent variable. So these are all happiness scores, whether they're actual or predicted or not. So let's look at more, for instance, like we have, this one's pretty close here. We have 6.379 actual value, where it had predicted that was 6.347. So pretty close. We can go through each one of these and kind of see that our guesses aren't actually too wildly off. So let's go ahead and plot this regression so we can see what it looks like visually. Just like the other chunks that we've been doing, I'll pretty much be copying and pasting everything that I have written from the previous episodes. One of the really nice things about data analysis is that once you have the code written and know how to do like something, then if you ever need to do that thing again in the future, you can just come back and copy and paste your original code. So in a new code block, let's set up our actual graph. I'll make it here, and now we can set it up. So I'll make our original points a scatter. So I'll say plt.scatter, and we want to pass in our training values because this is like the bulk of our data set. We'll say xtrain and then ytrain. And then we want to plot the line of our regression. So to do that, we'll do plt.plot like this. And we're going to pass in the x values for happiness score, and then also the predictions. So, or sorry, these are x values for economy, not happiness score. And then we have our predictions here, which will be for happiness score. And then just like we did in the last episode, we'll want to make our line extend to both ends of the graph so it doesn't just stop abruptly. So to do that, we're going to call plt.axLine. And then we're going to set our intercept coordinate to the intercept, which should be 0, and then a float of our intercept, like this. And then we would like our slope argument to also be equal to a float. And that's just going to be the coefficient / slope like this. And it'll probably help if I spelled linear right. It might be a little bit better. Okay, and then, of course, as always, let's add our labels. We'll do plt.x label is economy. plt.y label is happiness score, and then we'll make plt.title equal to happiness score versus economy. And then at the very bottom of this, we'll type plt.show. And then let's actually run this now and see what we got. So if we run this, we now have a solid linear regression graph. The points represent the scatter plot of our training data, which is meant to represent the majority of the entries, and the line represents our model or our linear regression model, which is meant to follow the trend that minimizes the variance of these points. And you can see, I think it does a pretty good job of actually minimizing them, because it looks like this line tends to follow the trend of these dots fairly well. Now that we have this graph, let's look at a few other linear regression models, which we'll get through a little bit quicker. Let's just go up here, actually to the very top where we trained it and tested it. Let's actually just change one aspect of it. Instead of using economy, let's use health. So in this sense, we'll be looking at how health can impact the overall happiness of a country. So I'm actually just going to change this here to health like this. And then let's run it and run all the blocks below it. So I'll run it, actually make our model and train it. Let's print off our line here. I'll just change this here. So this new slope would be, let's see, we have 3.81 like this, plus 3.28. So that'll be our new linear regression line using health instead of economy. And then I'll run this to get our new score. Let's see, our score is a little bit lower, which is okay for now because we'll look at that in a second. And then let's just run our predictions again. And here we go. Here is our table of predictions. And then let's actually just print this off here like this. And I'll also want to change these X labels and Y labels to actually match what we're doing, and same with the title. But actually, I might do a quick improvement here. Here's actually what I'll do. So I'm going to go back up to the top here, and I'm going to make a variable. I'm going to call it xvar, set it equal to, actually I'll do xvar and yvar. So we have both of these. And then I'll just store health in this one, and then happiness score in this one. And the idea with doing this is that if we want to change the variables, we don't need to change them in every single field, like changing them in here and then also labels and everywhere else. We can just change it up here and then plug this variable in for every time we reference it. So now instead of passing in strings for all these, let's actually pass in this variable anytime we want to use it. So here we're going to pass in xvar. Here we're going to pass in yvar. Let's go down a little bit. Looks like we don't reference it here. And then we want to pass in for our X label, we want to have xvar. Y label, we want to have yvar. And then obviously for our title, we want to have something, actually let's remove these here. I'll do something kind of neat here. I'll just do, let's say yvar plus, then versus like this, and then plus xvar like that. And then so the idea with this is that if we were actually to go up here and just run this block now, retrain our model, let's rerun everything real quick, get scores again, get predictions again, and then run our graph now. We don't need to worry about having to change the labels by hand because we just stored them in these yvar and xvar variables. So now they're super easy to access and change whenever we want. So we're just changing one line instead of like 50. So if we look at this graph and compare it to the graph we had versus economy, it appears that this actually is pretty similar to our economy graph with a fairly tight fit and positive correlation between the two variables, that being happiness score and health. I want to look at one last correlation though, and that's the correlation between economy and health. In this case, we want economy to be our X variable and health to be our Y variable. So let's change that up here. Let's say economy for our X variable, and then we will have health for our Y variable. And then let's all run these all again. Run this here. Let's get our score. We got 0.61. Let's run our predictions. And then let's run our graph here. And now we have health versus economy. It seems pretty clear based on our score in this graph that there actually does appear to be a pretty strong correlation between the two of these variables, being health and economy. And it appears, again, like our score here is 0.61, which is not like amazing, but it's definitely not bad either. So it definitely is some sort of positive correlation between these two variables. So basically, in conclusion of all these simple linear regressions, what do all these say about our data set? Well, it says that a country's economy and health scores are likely the two biggest influencers of a country's overall happiness scores. And also, we found that a higher economy score is generally correlated to a higher health score for an individual country. So let's look at one last thing before I wrap up this video. Let's take a look at a multiple linear regression with more variables than one. So let's actually go back up here where we're making our model and training it. And let's modify the X variable here. So let's change our Y variable back to happiness score real quick. We want to look at happiness score. And then let's think about what X variables we want to actually include in our multiple regression. I'm thinking since we went over economy and happiness, we should combine those two together and then also add in family. Because if we look at our Seaborn plot here, go up. If we look at, so economy, family, and health are these three columns side by side, so columns 3, 4, and 5. If we look at their correlation with happiness score, they all appear to be pretty heavily correlated, at least reasonably. So let's actually combine those three in a multiple linear regression. So I'm going to go back down here to our model. And then I'm just going to make our xvar a list instead of just one string. So I'm going to say, have it be economy, health, and then family like this. So now we're basically combining the economy column, the health column, and the family column, all to predict the happiness score. And then the only change I need to make to this is to get rid of this reshape function, because we only need to reshape if it's one dimensional, but it's not since we're selecting multiple columns. So now let's actually train and run this model. Let's run it here. Now we've made our linear regression. Let's look at our coefficients at intercept. So we have three coefficients here. Obviously, we have one for each variable. So this would be our coefficient for economy. This would be our coefficient for health, and this would be our coefficient for family. And then, of course, like usual, we have our one y-intercept value. Let's look at the score now and see what we got. Okay, so nice. We got a score of 0.768. So that is actually the highest score I believe we've gotten so far with all of our models. Let's actually run it a few times just to see kind of what the average score is. So we got 0.76, we got 7380. That's nice. 76, 71, and okay, that one's a little bit lower. 48, that one's really low actually. It's getting lower and lower. Let's see, that's 0.68. Okay, so actually, if you notice that whenever you run it over and over, it seems that the average score seems to generally be higher than that of a simple linear regression model. This is generally the case when we add more variables into the mix because it gives our model more data to train on, and it looks like this multiple linear regression model actually is more accurate than the simple ones we've gone over so far. And that pretty much sums up everything we're going to cover in this video. Just like last time, I'll do a simple kind of analysis of this data set and kind of what the conclusions we've come to are. So basically, looking at the data set with the World Happiness Index, it appears that the variables of economy, health, and family are the three most strongly correlated to the overall happiness of a country. Where it looks like economy is probably the overall highest correlated on its own, and then there also appears to be a correlation between economy and health, for instance. When combining the variables of economy and health and family together in a multiple linear regression, it looks like those three are the best predictors of the overall happiness score. So something like that with what I just said would be a nice little succinct way to kind of summarize the data set and kind of summarize your findings using some analysis and predictive modeling. And that's going to officially wrap up this course for you guys. I really hope you're able to learn a lot about data analysis, and I hope that this course was comprehensive enough to at least give you started on your way. Give yourself a pat on the back if you've gotten this far, because this stuff isn't always easy and can be challenging and intimidating at times, so I certainly respect it if you've gotten this far in the course. In the future, I'll be making more courses like this, so if this kind of stuff helps you out, please subscribe and I'll keep pumping this stuff out for all you guys to see. Take care, everyone, and hopefully I'll see you in my other videos. Peace out.